vai estar checando pronúncia de ninguém e nem se preocupando com erros de gramática. O inglês aqui é só um mecanismo de comunicação e assim dizer, criar a cooperação, possibilitar essa cooperação. Now I'm going back to English. I was just saying to everybody, Maria, that they don't need to worry about English mistakes and bad pronunciation. We are just worried about communication that can build an even stronger relationship and cooperation that we already have with University of Essex. I would like to thank the presence of Carlos Ribeiro, the head of Computer Science Division, and all the present people here. This event is the result of the joint effort by several professors, students, and employees. I would like to thank them all. I'd like to thank Elton Sbruzzi, the Big Data Science Lab. He's part of the Big Data Science Lab. I'd like to thank also the Print Data Science Project that enabled the visit of Maria Fazli to ITA, the Computer Science Division, ITA, and also the Human Science Technology Engineering, Mathematics, Manufacturing, and Design project that is part of this event also, but is going to take place tomorrow. Today, we are going to see some selected works that are currently in progress at ITA related to data science in general. Tomorrow in the morning, we are going to have some presentations related to data science, but focused on pandemic, and let me check the name of the event. The project Data Science Coping with Pandemics, Epidemics, and Outbreak in Brazilian Hospital. It's a project coordinated by Professor Ana Lorena. It's going to take place tomorrow in the morning. And there is a keynote session by Professor André Carvalho from USP São Carlos. You are all invited to come. Tomorrow in the afternoon, we are going to have the Human and STEM 2D, where we are going to have also another presentation from Maria Fazli related to human in technology and science. Thank you very much. And we are now starting our presentations. I would like to invite to present the paper, A Composable Machine Learning Approach for Classification and Simulation of Cancer Treatment Response. That's going to be presented by Lucas Povoa. Lucas, please.
Hello everyone, good morning. Thank you for coming, and I appreciate everyone here. So, I'm Lucas Venezian Povoa. Today I will present my PhD thesis called A Composable Machine Learning Approach for Classification and Simulation of Cancer Treatment Response. This work was developed in the context of a partnership between ITA and the AC Camargo Cancer Center. So, I've divided my presentation in 4 main topics: introduction, then I will present the multi-learning training approach that we developed to solve some problems related to cancer. Then we will present 2 case studies in cancer, and then we provide you the final remarks showing some contributions and limitations of your work. Obrigado. And point for some future work. Can you hear me? No? Nice. Thank you. So, our introduction. That's important to know that cancer contributes to a large number of deaths worldwide. That's very important information and have a lot of opportunities to improve the quality of life of people. So, for example, cancer fatally reached more than 4 million people by 2018. That's a very expressive number, with projection of 19.8 million new cases per year for 2025. Then, behind that, cancers are caused by change in the DNA. That's its mechanism. It's important to know that impact that is caused in the body that occur over the course of individual lifetime. That's important because when we apply machine learning to identify some group risk or treatment response, that implies in how we can treat the data around the subject. On the other hand, in a technical side, cancer provides several statistical and computational challenges, as it usually relates to data sets with few samples, a lot of variables, a lot of missing data, and so on. That's a very challenging problem. In a specific view, we can highlight the multiple myeloma. That is a cancer of plasma cells, the second neoplasma being more common and considered an incurable disease. Multiple myeloma patients unfortunately have a mean survival of 5 years. That's a very challenging disease too. Multiple myeloma is characterized by heterogeneity in the clinical outcome. That's another important information. Finally, we can highlight in the scientific perspective the number of publications related to machine learning applied to cancer that is growing fast in the last years. It could provide us a better context and a lot of related work to provide some support for our research. Okay, here is our objective. We want to define a composable machine learning approach to classify and simulate the treatment response of cancer patients based on statistical and machine learning techniques. That's a very important statement, because the idea behind the composable term is that we can extend, based on data requirements, our approach, combine new methods and learning approach, supervised, self-supervised, supervised, and so on, to create a more robust representation of data and then improving the accuracy of our models. Okay, the multi-learning training approach, MULT, we call it MULT. What's the idea? What's the overview about our approach? That's a CMLA that combines supervised, self-supervised, and unsupervised learning algorithms compressed in two integrative ideas. First, combine clinical marks, gene expression levels, and treatment to compose a more sophisticated patient descriptions. In a general way, we can state that the current practice in the clinical decision-making process use mainly clinical data, not using gene expressions in a large way. 2, create new representation of gene expression levels based on different learning algorithms in order to find hidden predictive information. So, we defined our multi-approach in terms of input, output, modules, data and processing components, methods, and then data flow. This is our structure. We use patient information, segregating 3 parts: molecular features, clinical features, and treatment. That the treatment separate of the other variables is very important because we need to simulate the better response. We have the first module, feature selection, that we segregate in molecular feature selection and clinical feature selection. The feature selection of these data sets is performed individually. Then we have the feature extraction module that have the components of patient clustering, that use k-means to perform that operation, gene clustering, and then gene encoding, that use the deep denoising autoencoder model. That last component is very important because gene expression levels have a process based on sampling that can provide a lot of noise in our data set. The DDA model aims to provide us a better representation of the data, resilient to noise. Then we have the treatment response classification, TRC, that outputs the treatment response score, where 1 represents a high probability of a patient to respond positive response to a treatment. So, feature types. Molecular features component is composed by gene expression levels mainly, that tries to measure the expression level of mRNA in a cell population in a certain time. Clinical features are composed by the descriptions, variables that describe the profile, clinical condition of patient, gender, age, existence of transplant, and so on. And the last component of our input, treatment component, is composed by data that describes which drug or treatment protocol the patient was submitted in the first-line treatment in your case. Focusing on feature selection, XFS, that's our selection algorithm, has three main requirements. One, choose features that are helpful to discriminate low and high risk patients. Two, avoid features with redundant information. That's very important to simplify the classification problems for our models. And three, avoid features that only segregate a particular set of patients. We want to avoid biased features. It executes the following steps to select features. One, perform a differential expression for each input feature compared to the response variable, generating p-values. Lower p-values is better for a variable in this case. Two, pairwise compare linear relationship between input features. Select input features based on the lowest p-values, excluding the lowest features with higher linear correlation when compared to a better feature. We want to avoid redundant information. That's the idea of this step. And finally, the algorithm performs a process using 5-fold CV and only select features present in all CV rounds. We try to avoid redundant information and that one specialized in some subject of your patients. The feature extraction model. We propose the PC component, the first component of this model, to detect clusters of patients with similar molecular profile. The GC component aims to detect pairwise relationship among genes. And the GE component aims to create a noise-resilient representation of your data. We put all of this data together and then send to the next model of your approach. Finally, the TRC takes as input the concatenation of the treatment features, selected clinical markers, outputs of the feature extraction model, and the treatment response marker to create the final predictor that outputs the treatment response score. Okay, cancer case studies. We have two cancer case studies here, and we start by presenting the datasets and implementation around that. First, all datasets are publicly available all of your experiments are reproducible based on open source code, okay? The datasets are from gene expression animals, and the multiple myeloma dataset is from MMRF composite studies. This is a big study organized by different companies around the world. For the last dataset, we created a code to collect dataset data and organize it. Okay. That's important to understand that for each dataset we have different variables, outcome variables too, and we need to create a specific rule to create the treatment response marker for each dataset we have. Okay. So, as important metadata, we can highlight the missing values in each dataset that is ranging from 0 to 12%, and overlapping class that bring the higher challenge for classifying multiple myeloma or cancer patients. Okay. As example, I can show you that figure that use white space to represent missing values and black space to represent fitted values. And as you can observe, we have a lot of missing values, and It's not easy to classify the data, the patient based on that, okay? And it's the rule, it's not exception. That's the point. That's the idea behind all that model I described before, okay? So, in terms of implementation, we use Python. I don't know another language that can fit better or challenge here, okay? That's very good. And use the pandas, scikit-learn, and TensorFlow, and Jupyter as a development environment for our experiments. That's pretty good. And in order to improve the quality of our graphs, we use R, the library ggplot2. I don't know another library to get us the same quality, okay? Again, all of our source codes are available at GitHub, and you can run the code and the dataset will be downloaded and we run and get the same results we present to you, okay? That's another important characteristic. So, evaluation methodology, okay? In order to directly compare multi-performance, we defined 4 baseline approaches, which are a multivariant called SMLA. We just removed the feature extraction module of our approach to simplify the process and to ensure some fair comparison with another methods that we use KNN, LightGBM, MLP, and SVM. Another important information is that we employ the Bayesian optimization algorithm to optimize the classifier hyperparameters. We use the log loss functions to be optimized, minimized in that case, okay? And use that process for all methods in the same circumstance and avoiding to look for the test data, okay? And finally, all experiments we will present to you in the next slides were based in a 5-fold cross-validation process to ensure that our result is not biased, or at least the best effort to avoid biased results, okay? So, the first study case, treatment response classification. We used 3 data sets in that study case, and we explored the performance based on 2 different perspectives. First, classification performance based on AUC metric, and 2, classification complex reduction. Here is important to highlight that we don't use confusion matrix because we need to define a threshold for our models. And to define that can bring another challenge that's not helpful in the context optimization that we'll show in the next part. Okay, what we can observe in that figure. Multi outperformed the baseline algorithms on the free analyzed data sets. That's a small difference, but Multi improved the result. In terms of absolute numbers, Multi correctly classify 108 more lives compared to baseline methods. That's very important for the hospital or cancer centers. And then Multi has better relative performance for data sets with smaller sample, more missing values, and more overlapping classes. That's another advantage. As harder our data set is, better Multi works. And the classification complexity analysis, I will resume that idea. We measure the complexity of the raw data set and compare that with the data generated by the feature extraction model. And then we could conclude that Multi provide a way to reduce the classification complexity of the provided data set. That's a very important because it's not the final result, but intermediary result that can drive another research and so on. And the second study case, the multiple myeloma. Here we aim to understand better how Multi can help the clinical decision-making process. That's a different perspective. That's the application of the machine learning model to understand how it could be applied in the daily lives of the doctors and patients and so on. Okay? So we use three ideas to understand that. We compare the capacity of gene expression levels, predicting mutation markers solver. That's very important because the current clinical practice use only fish markers in the market, okay? Change that's not easy, and understand if gene expression can predict if fish is a very important information. We try to understand the relationship between features, and then treatment response simulation to identify which treatment could benefit more a patient. So, here we can observe in that figure that when using gene expression to classify, to predict fish markers, we achieved a AUC of 94 in average. That's a very expressive result. Oh, that is, gene expression can predict fish, and you can change that information in the practice. Then other results. We use a graph representation of the features in a try to better understand the relationship between them. So, triangles and circles represent clinical markers and genes, respectively, okay? While color intensity is inverse proportional to average p-value. So, as centralized features can represent more important features, okay? And we can highlight the gene features that in numbers is more important and relevant than clinical features, but some of the clinical features can bring a lot of information more relevant than genes in general way. So the transplant information is the more important marker here. And finally, we develop an optimization algorithm to use in Multi to identify which treatment could bring better opportunity to patient response to the treatment. And we identify that more than 25% of the results could be patients could get a benefit from another treatment. Okay, contributions. Our experiments consider 4 different and independent public data sets. We evaluate and compare Multi along 3 different perspectives. We try to explore a clinical decision-making process to use Multi as a support tool for the practical in the hospitals and cancer centers. And we observe in our results that Multi had the best classification performance. And finally, our experiments are reproducible via source codes, okay, publicly available. Limitations, lack of more robust cancer data sets, that's very hard and costly. Lack of independent validation with data sets generated in the same parameters and independently when compared to employed in your experiments. And Multi was limited to binary classification, and then current Multi implementation contains static hyperparameters that can be optimized. Some feature works, generalization of Multi, investigate more treatment, extend Multi by add medical image, deeper explorer, perform new experiments, use different feature selection algorithms. Thank you very much.
Thank you. Thank you. Someone has any questions? We are kind of running late, so if there is no questions, please.
About the feedback that you used to select, Leonardo. You used it before the... Okay, where did you...
Obrigado. Esse daqui é o pointer, né? Ele funciona.
Okay, I got it. We split the data set based on our response variable, okay? And we get a group marked with 1 and another group marked with 0, okay? And then we apply a KS test to understand if the distributions are equals or not, okay? And then we get that p-values for each variable.
All right, thank you.
Okay, thank you very much.
We are going now to have the presentation from Leonardo Silveira.
Hello, everyone. Thank you for having me. So my name is Leonardo Silveira, and I'm very excited to be here today presenting the research I have been working on with Professor Felipe. And the name of our research is latent graph inference from unstructured data. So starting with a quick motivation, most data that we generate and that we have available to us is unstructured, meaning that we don't know the entities that are represented by the data, or if we do know the entities, we don't know how they are related together. For example, when we have an image, the only information that we have is the pixel intensities of that image. But if we, humans, are in a park and we see an image like that, two kids skating, it's very natural for us to create a structure for the scene. We are able to understand what are the important objects and how they relate together, and also how their relationship may affect the future state of this system. And if you think about it, this is a way we humans understand the world around us. We understand it in terms of objects and their relationships. And this is a very powerful abstraction. And we argue that the development of models capable of understanding the environment around us in terms of objects and their relationships is an important step in the quest to develop machines with human-like intelligence. So this is a big topic that we may call structured world discovery, but it's a problem that is too hard. So what we usually do is to break it into smaller problems. The first one is object discovery. Given raw sensory data, how we can extract the entities of this data, the objects that are represented by this data. And the second problem is latent graph inference. Given the objects of the data, how we can discover the structure that glue together these objects. And in this second problem is the problem that we will be talking and focusing today. So how can we go about trying to discover the latent graph from some data? So the most simple approach that we can take is to assume that one entity of the data is connected to all other entities, so that we have a fully connected graph. And this approach is inspired by the literature of self-attention. And it's once we have a fully connected graph, what we can do is to attach an attention coefficient to every edge in this graph. And then we let the learning process decide what are the important information, what are the important connections, and what connections are not important. So it's a very simple approach, but it has some limitations. And the main one that I would like to highlight here is that it does not capture the sparse nature of most real-world graphs, right? The graphs that we find in nature, they don't have this densely connected topology. A better approach and a more sophisticated one would be to leverage the variational autoencoder architecture. So if you recall, a variational autoencoder is composed by two parts, an encoder and a decoder, which are trained jointly to perform some machine learning task in the end. And in this setting, the encoder receives unstructured data, that is the entities of the data and their features, and extract from this data a latent graph. And this latent graph is then fed into a decoder, which learns the node embeddings, the latent node embeddings to a machine learning problem. And this architecture has many positive aspects. One that I would like to highlight is that we can explicitly extract the latent graph from the data. So after the model is trained, we can get this latent graph and do, for example, characterization of this latent graph. We can, for example, look for communities in the graph. But even though it's a very good model, it also has some shortcomings. And the two that I would like to highlight is that this model, the variational autoencoder, in the vanilla format, it assumes that the edges of the graph are generated independently. This assumption does not hold in real life. The second limitation is that this approach is able to scale over to hundreds of nodes. And for the things to start getting interesting, you need to go beyond this scale. And lastly, one last limitation that I would like to highlight in the current state-of-the-art methods is that they are only able to model static graphs. And what I mean by that is that if you have a graph that evolves over time, for example, the edges between the entities change over time, you might not be able to model these phenomena. For example, if here is a human skeleton performing the walking movement, and it has been shown that the optimal graph that is able to predict the position of the joints of the skeleton changes as the skeleton takes the left and right step. And so if you have some effect like this, you are not able to extract it. So we have seen until now the state-of-the-art approach and some of their limitations. And what we are going to try to do is to propose a method capable of filling some of these gaps. Our method has 3 requisites, which are must-haves for the method. The first one is that it must explicitly infer the latent graph, as the variational autoencoder does. It must be able to model dynamic relations between the edges of the graph. And thirdly, the method must account for dependencies between the edges of the graph. These are the 3 must-haves of our model. And one thing that would be a nice to have is that the model is able to scale to the thousands of nodes, which is where things start getting interesting. So this is what we are going to try to achieve and how we are going to try to do it. So we are going to formalize our model as a variational autoencoder with an encoder receiving the unstructured data, outputting a latent graph, and this latent graph being inputted in the decoder. Choosing this architecture, one of our objectives we can already achieve, which is to extract explicitly the latent graph from the data. So this one was easy. But now we need to look for the 2 parts, the encoder and our decoder. We have seen that this approach is not able to take into account edge dependencies. So we will have to replace the traditional encoder of the variational autoencoder to something else. And one promising avenue of work here is to use an autoregressive generative model as our encoder. So what is an autoregressive generative model? It's a generative model for graphs that add elements to the graph, the nodes and edges sequentially. So for example here, we add the node 1, the node 2, connected both. Then we add node 3 and decided that it would connect to node 1 but not to node 2. And an important characteristic to take into account here is that, for example, in this 3rd step, the elements that are being added here are dependent of everything that was added before it. So this method has baked into it that the elements will be dependent of other elements. So if we are able to make an autoregressive model to work as our encoder, we are able to model edge dependencies. And to do this, we will model our decoder using recurrent neural networks, inspired by the work of Yu et al. We will use two-level RNN. The first level, which is in blue here, each RNN unit will create a node in the graph. And when a node is created, it goes to a second level where each RNN unit will create an edge in this graph. I won't go into details here because of the time, but we can talk later if you wish. So we have our decoder that will be an autoregressive model using recurrent neural networks. And this grants us 2 characteristics that are objectives for our research. The first one is the model is able to model edge dependencies, and it also, another important point here, is that when these autoregressive models using recurrent neural networks were first proposed, they were able to scale to more than 2,000 nodes. So this is a good indication that our model will be able to scale to this number of nodes as well. So now we got 3 of the 4 objectives that we stated before. We are able to explicitly extract the latent graph, model edge dependencies, and scale to the thousands of nodes. And we will have our latent graph here, and this latent graph will be fed into the decoder of the model. So once the decoder receives a latent graph as its input, we can note that any GNN pipeline, any graph neural network pipeline will work here. But we want that our model our model to be able to take into account dynamic changes in the edges of the graph. So the graph neural network layers that we have off the shelf do not suit our needs here. We need something else. And to do that, we propose the mechanism. And the intuition of this mechanism is the following. Imagine that you are watching a sports game, or for example, a football match, and there is a graph that represents the players. There's an underlying graph here. And every player is a node of this graph. And there are edges connecting the players that have a relationship to each other. And as the players move in the field and pass the ball to one another, some edges of this graph will appear and other edges will disappear. It's like there's a little switch in every edge and the edges can be switched on and switched off. So this is the phenomena that we want to be able to model. For this, we proposed a mechanism called the switch gate. The switch gate will be attached to every node in the graph, and it will receive the embeddings, which is the state of the nodes which are connected by that link. For example, here there's the switch gate AB, which is in the link in the edge that connects node A and B. The switch gate will receive the embeddings, which is the state of node A and B, and based on this state, we will decide if this edge will be on or off. It will work following this equation, so the embeddings will be concatenated, and then they will pass through a single layer perceptron, and finally through a sigmoid nonlinearity. And the function of the sigmoid here is to make it very easy for the switch gate to turn off the edge just by making its argument very negative, or turn on the edge just by making its argument very positive. And the deployment of the switch gate in a neural network layer is very similar of that of an attention coefficient. So it can be very easily, it can be deployed very easily with most graph neural network layers. Here is, for example, in the equation of the GNN layer proposed by Scarcelli. We can see that as we aggregate the embeddings of the neighbors of node A, every embedding is multiplied by its switch gate, and if the switch gate is 0, it's like that node doesn't exist. If the switch gate is 1, everything goes as usual. So this is how our decoder will be able to work. And now we have described every component of our architecture. We will be able to explicitly extract the latent graph, filling one of our boxes. Our encoder is a autoregressive model. We will be able to model edge dependencies and perhaps be able to scale to more than 2,000 nodes. And finally, our decoder, we will use this mechanism. And it's important to note that this switch gate will be employed in a pipeline of graph neural networks. So we can vary here how many layers we want. And hopefully, using the switch gate, we'll be able to model dynamic graphs. So Felipe and I, we just finished working on the details of this graph, and we will start simulating in the next month. At least in paper, we are filling all the boxes that we set out to do. So hopefully, this model will be able to put us one step forward in the path to having models that are able to describe the world around us. Thank you.
Thank you, Leonardo. We have time for questions. Thank you, Leonardo. If you don't have questions, I'm going to proceed to the next presentation by Pedro. Pedro? Okay. Pedro Paiva is going to present the study Hardness and Embedding of Datasets, a framework for relating data, characteristics, and learning performance.
Okay. Okay, good morning all. It's a pleasure to be here presenting our work for this workshop. My name is Pedro Paiva, and the title of our work is Hardness Embeddings of Datasets Relating Data Characteristics and Learning Performance. Professor Lorena is my supervisor, and I am a PhD student at ITA in the Computer Science Department. So, I will begin with some motivation, and I will bring also some motivational questions to justify the how can this work make some progress or some step towards the data-centric modeling approach we are seeing today. It's a new trend now. In December, we are going to also present a paper in the data-centric AI workshop of NeurIPS, who's one of the chairs is Professor Andrew Nighi, which is an exponent in machine learning, and now this topic of data-centric approach. So, for building successful machine learning system, it is imperative to have both high quality and well-tuned learning models. We can justify this, the first part of this sentence, high quality data, with the popular saying that garbage in, garbage out. If we give garbage to our model, regardless of this model being a really advanced model, but if we give a garbage data, we then get a garbage at the output. On the other side, we need a well-tuned learning model with, for example, optimized hyperparameters and so on. And the model-centric approach, it is well known, but this part of the data is also important. That's one main argument that we bring here. So, but how can one assess the quality of a given data set? This is a good question, because normally what we have is some results that are usually summarized through average statistics. For example, we train a model, and then we verify some value of, for example, RMSE or and so on, some metric. But that, in some cases, in most cases, in real case, that's not enough just to have a summary statistic. But rather, we want to investigate further why, for example, some instances in a data set are harder or easier to classify, for example. In the scope of this work, we are talking now just about classifiers, but we are going to extend this to regression models as well. And how can the strengths and the weaknesses of a model along a data set be revealed? So we also want to analyze which part of a data set, for example, is well, for example, how can a classifier have a good performance in part of a data set or a worse performance in another part of this data set? Because we know that models have they have different bias. They are constructed based on different biases. This is, and for example, a linear model or non-linear model and so on. And this investigation is also interesting to, for example, compose an ensemble of models for a given task. So now I'm going to talk about ISA framework, which is the start point of this work. So a recent meta-learning methodology known as instance-based analysis, or ISA, was proposed for visualizing algorithm performance across different data sets. So ISA is a meta-learning approach. So it takes a set of data sets and project. Basically, ISA is an embedding. We are going to produce a two-dimensional space where we can see a bunch of data sets and compare them. So it generates a two-dimensional projection relating meta features, values, and algorithm performance, such that we can see that there's a property of the instance space that the observations are distributed more or less linearly regarding how hard they are to be classified. So we preserve, let's say, a hardness ordering of the observations along this projection. So here we can see an example of an instance space where we have the observation here in a classical meta-learning approach. Each point in this space corresponds to an entire data set. And observations, as I said, are distributed linearly regarding how hard they are to classify. So for example, the color here is the instance hardness and indicates this distribution. And that's, in the next slides, I'm going to talk why this is an interesting property of the instance space. So the proposal of this work is then to use the instance space analysis in a more fine-grained analysis, but rather, instead of using a bunch of data sets and projecting the instance space, we are going to take only one data set and making a one-to-one mapping, so where each instance of a data set is an instance in this instance space. And in this way, we expected to have a tool for visualizing and investigating why some instance of a data set are harder or easier to classify. And we expect that this gives us some insights about the data, because we are really concerned about the data quality. Because investigating the data quality will reveal some data issues, just like biases and unbalanced classes or class noise, etc. And the benefits are twofold: insight on data quality issues, as I said, and we can now see the weaknesses and strengths of different models by a measure that is based on a footprint, which is an area where an algorithm performs well in this instance space. So we can measure how well an algorithm is performing for this classification data set. So this figure here presents a general framework of our work. What we do here is we take the original data set D and extract a set of hardness measures. And hardness measures I intend to reveal or to somehow predict which instance will be harder or easier to classify without actually trying to classify it and trying to train a model. But we also have another path here, which is composed by a pool of algorithms, which is the algorithm space. So we have a list of classifiers, and applying those classifiers to the original data set, what we get here is the performance space. So we have, for one instance, we have some performance metrics, for instance, log loss. We have a feature selection step here, which considers the performance space to select the best hardness measures which predict the hardness of an instance. And they are put together to compose a metadata set. This metadata set is then the input used for the instance space. So here we have the original instance space formulation as proposed originally, and then we got an instance space where we can see each instance or each observation of the data set in this space and investigate it. So this is our developed tool, PyHard. And PyHard is basically, it implements this framework here, is implementing PyHard. So from the beginning, from the original data set until the instance space is generated. And then we have also an application or a graphical interface where the user can interact with this instance space. At the left we can see, for example, a principal component just for comparison, and we have the instance space of this data set. But how can we extract insights from that application? The methodology the user can, for example, select areas of the instance space. For example, this green area here is a footprint. So as I said, this is, for example, a footprint where an algorithm or a classifier performs well. So instances outside this footprint normally are harder to classify. So the algorithms have struggled with this instance here. And then we can select then, and our tool also plots some some distributions here, for example, box plots or histograms, and we can see how the features and the meta features and the performances of the classifiers are behaving in this sub-area of our space. And using this methodology, we expect to extract those insights that I've told about. So I do not present here because I'm just present the general picture of our framework, but we also have some study cases for COVID data sets, and we also used it as a proof of concept with Compass data set, which is a non-data set that has biases, in this case race bias. And this solution, so our idea is to give research a complete solution from an end-to-end solution to investigate the quality of the data. This is the main reference of our work, the work from Munoz et al. And our repository, our work is available in this repository at GitLab, and we also provide a package in PyPy where everybody can download it and use it through command line to try different data sets. So thank you.
Thank you, Pedro. Moving on, we are now having another presentation. I'd like to invite Douglas. Roberto Douglas is going to present the study SLEDge Score, cluster evaluation based on semantic analysis.
Não tá aqui, isso aqui. Eu acho que é outro. Okay. Deixa eu mudar aqui. Acho que é. Ponto aqui, né? Good morning. Thank you for coming. My name is Douglas Aquino. I will present a part of my thesis. The proposed is SLEDge Score, the clustering evaluation based on semantic analysis. Is a part of my thesis is related with machine learning, specifically clustering and unsupervised learning. Is developed by me, Professor Vitor, and Professor Felipe. We'll talking clustering, a briefing. It's some information. Clustering, cluster analysis, the SLEDge Score, some results, and a conclusion. Clustering is useful in several exploratory strategies. By, for example, pattern analysis, grouping, decision-making, and machine learning situation, including data mining, document retrieval, image segmentation, and pattern classification. In many such problems, there is a little prior information available about the data, and the decision maker must have a few assumptions about data as possible. It's under these restrictions that cluster methodology is particularly appropriate for the exploration of the interrelationships among the data points to make an assessment of their structure. Sorry. So, over the last century, some works have proposed methods for analyzing the quality of the clusters using different strategies. Euclidean distance, is Euclidean space, it's most used by the most works. For example, Kalinske and Harabas that performs cluster analysis based on point dispersion, calculate by the sum of the squares distance for their centroid of the points. And Rousseau, it's proposed a metric called SLEDge Score in a graphical tool for evaluation the quality of the clusters based on the grade of dissimilarity between points. It's about degrees of belonging of the points. So we propose the SLEDge that mean support length, exclusivity, and difference for group evaluation. It's a method that suggests an internal validation for evaluation that use frequent patterns mining inside of the groups to evaluate the cluster, the quality of the cluster. Don't use distance metrics, so it's a different proposed, a different approach. So, but requires that the data be in a categorical form. So, we have some steps to execute the SLEDge. First, semantic descriptors that the algorithm identify frequent patterns using data mining. So in each group, we have a SIG, that means a probability of frequent pattern I in group G. In the second step, we have a particularization with when the main frequent patterns are selected. And we use these criteria. SEG, calculate in the another step. SIG is more than SIK plus U minus G. When this is a criterion to keep I in group G when comparing with the others N minus N groups with K different G. when U means G is 1 divided and minus 1, summatory, SIK, when K different G. If SIK is low, I is kept in G, it has a great potential in describe the group. If SIK is high, is not strong enough to describe the group. Group G in is removed. So after the first and second step, we have now a SLEDge score. Sorry, a SLEDge score when we have the 4 indices to calculate. A SLEDge score is made up for these indices. SUP, or support, is our average support of FPG, when FPG is a set of frequent patterns in group G after particularization. So, SUP is average support FPG. We have a weight for support. We believe that groups with high support are best. So, Len, this formula is 1 divided by 1 plus absolute value between the difference, the FPG size and FP average size. This is a weight for group length. We believe that groups with average length are best. Exclusivity is equal 1 minus number of non-exclusive I in FPG divided by FPG size. We have a weight for exclusivity. Groups with exclusive frequent patterns are best. And finally, the diff is a maximum difference in FPG support. We have a weight for support difference. We believe that group with variable support are best. Finally, we calculate the harmonic mean of these indices, and we have the SLEDge score. We have an application, a little application, in using the IRIS database, well-known IRIS database, and we will use this algorithm, clustering algorithm. K-means is a partitional strategy, and then, the others is agglomerative clustering or hierarchical clustering with linkage word, average, single, and complete. We will use the SLEDge score and SLEDge with evaluation method. How SLEDge requires that the database be in categorical form. We divided the database into these ranges for application. So, as we can see, the different algorithm and behaviors by the scores. The SLEDge score is blue. We can observe that is a ascending behavior as k is a number of clusters, is increased. SLEDge score is a red curve, and we can observe descending behavior. So we can use both scores to evaluation. Yeah. So we have k-means, agglomerative clustering with linkage word, average, and we can see others algorithm. Here we have interest information. When we use algorithm with linkage complete, this dataset has three classifications, three groups, and the SLEDge score can identify, for example, some information here. The silhouette score don't be clear. So we believe that contribution, given the approach, regardless of the distance metrics suggested by the SLEDge score, we believe that was a great potential to contribute together with the other methods to a more clear and precise assessment of the quality of the clusters. For future step, we will develop an application in other database. We will realize a statistical validation and a graphical tool like a silhouette score. This reference used in the presentation, and thank you very much.
It's very interesting, Douglas. I'd like to ask you, how do you intend to validate your work? Because it seems to me that the SLEDge score is supposed to be bear in some sense of other methods to evaluate the cluster formation, but it's not very clear. It seems that a very good idea to try to use semantic analysis. I think that's really interesting. But how do you intend to validate the proposal?
We pretend use 20 another database different with structured different to realize the tests and the validation. Thank you.
Okay, thank you. Now we are going to have a presentation made by Daniela America da Silva. Daniela? The title of the study is Why Machine Learning Bias is Bad.
Onde que aponta aqui? Pra onde que eu vou? Ah, aqui, né? Aqui. Ah, tá. E aqui, não. Ah, tá. Ok.
Aqui você...
Tá. E o microfone. Usa esse aqui? Tá. Tá todo mundo me ouvindo? Tá? Ok. So hello everyone, I am Daniela. I am a PhD candidate in the almost in the last semester. And I'm studying machine learning bias as part of the model I'm proposing for my thesis that is based on asymmetries in the graduate courses in Brazil. So I have published one paper about offensive detection of offensive language in conversational AI. And I also have one more presentation at the University of São Paulo beginning of December, where I will be talking about AI ethics. So my supervisor is Professor Johnny Cardoso Marques, and my co-supervisor is Paulo Marcelo Tazinafo. So my work today is why machine learning bias is bad. So we know already that we have AI algorithms used in many tasks. We had so many presentations here about applications of machine learning. And this is an important subfield of artificial intelligence. So algorithms are often cheap, used at scale, and then are more likely to be implemented without process. Frequently, people, even us working with ML algorithms, we assume that algorithms are objective or error-free. Also, we are biased. So we may think why bias in algorithms could be a problem. So why machine learning bias is bad? So this is the question of this work. My motivation is to demonstrate the need for bias and discrimination detection in ML systems, and also present some methods that could be used to measure fairness in algorithms. So to find out, I will investigate that in 3 steps. So step 1 is about AI bias and discrimination. So algorithms are used differently than human decision makers. And the performance is linked to the quantity, quality, representativeness of the data. Also, developers need training, and they need diversity in the data to resemble the complexity of the real world. Also, machine learning can amplify bias if they are reinforcing things that are not always consistent with the reality. And then, when this bias is incorporated in our decisions, then this becomes discrimination. Bias is kind of a complex field because it's relative to task. For example, in healthcare, it's not a problem if the diagnosis is gender-oriented, but in higher, it could be discriminative. And then we need to be careful. And we need to identify and know what measure we are going to apply in different bias scenarios. So I brought some research here, 2 important papers discussing about social data, pitfalls and ethical boundaries, and also a framework to understand the source of harm in the machine learning life cycle. So talking about the data, about the social data, this paper maps at least 7 types of biases types. So data bias is when we have a systematic distortion in the sample data that compromises the representativeness of the data we are using. Population bias is related to distortion in the demographics. So we could have a user characteristics differences in let's say in a big country like like Brazil. Behavior bias, when the behavior of the user changes between platforms. Content production bias, that are most related to text generated. And then we could have structural differences. And this is one thing that I studied more deeper when I was studying NLP and offensive language. Linking bias is also related to the different attributes that could be used between the interactions of people. Temporal biases, modifications in behaviors over time, and also redundancy when you have duplicated data. This could also impact the algorithm. Sources of harm. You can start using ML algorithm and preparing a data that is perfect, measured. However, this could be emphasizing stereotypes. Representation bias. Your data could be underrepresented for some part of the population. Measure bias. You choose a feature, or you could choose a feature or labels that is approximating some idea, but is not representing some other groups. Aggregation bias, when you assume that the labels is consistent, but you could have subgroups that you didn't identify. Learning bias, when the model amplifies disparities. Evaluation bias, when the data does not represent the population that you use, the ML system. And deployment bias, when you construct something that is not related, it's not going to solve something for the population that will use it. Why we need fair in ML? Why ML should be fair? So it's important to support human values. So it's not only about algorithms. It's important to identify strengths and weaknesses of the system. So we need to monitor the systems that we are creating. We also need to track improvements over time, because the behavior of the system can change during the utilization with more data. However, it's not easy to come with a single way or definition for ML. There are multiple ways of implementing that. We could have a one-step decision. Could you hear me? Oh, yeah, okay. Let's try the other one. Okay. Okay. Oi? Foi. So then you could have a one-step decision-making step, and you could check how these decisions are impacting the underlying population. You could have an auditor to observe the decisions. And you could also verify the data stream classification. And how to categorize the different types of fairness in ML. Also, there is not a straight way. So one author that wrote about fairness definitions, he defined the categorization based in statistical methods, checking the predicted outcome and the predicted probabilities, or similarity based, or based on definitions for inferences. There is another categorization that could be used between directed and indirect discrimination. For example, directed discrimination is when a person is treated less favorably because of one attribute, let's say postal code, and indirect when there is a policy that applies to everyone, but there are some effects in some people, in some group of people. Individual and group, so individual, you measure the discrimination for each individual, and group, you measure the impact towards the group. And explainable and unexplainable. Explainable is when you can identify the differences between groups, And unexplainable is when the discrimination cannot be explained related to one group. So in the step 3, I'm going to present some examples found in areas where some issues were found. Some of them are well known. For example, we have this project, the gendershades.org, related to representation bias. They were testing Microsoft and IBM face detection systems, and they noted that they have a gap in the performance for the identification of black women photos. This was published, I think, in some years ago, so they made some corrections about that, but it's just an example on how algorithms could have a gap. Social bias, this is, I just got this screenshot yesterday. So this is about the autocomplete in Google. So I just put there, teachers are, and I tried with scientists are. And I started to identify what people are telling about these occupations. And I tried that in Portuguese and English. I brought in English here, but there are differences on how people see other people's occupation. Fortunately, we have, I think, good things here. Like teachers are superheroes, good thing. And like candles, this is a good one. There is one not so good here. Teachers are not okay. So if you just try one occupation in different languages, you could notice different interpretations in different regions of the world when they are using Google. Another one is the behavior bias. So these emojis, they are all the same, but they are used in different platforms. So when you are exchanging messages, in Google, for example, an apple emoji that could be happy could be interpreted as more negative or neutral in Google platform. So we could have miscommunication because we have differences between platforms and user behaviors. This was something very critical in US, the Compass risk prediction system about recidivism of crimes, where they detected that the minority communities, because they were often more policed, they have false positive rates, so they were rated in higher risk compared to other communities. So this is an example that happened when using machine learning for criminal sentences. The other example is the biobank. This is a study from UK. So this is from 2017. I didn't find recent information, but the problem here is that 96.4% of participants in the biobank were white, and they were generally older women and less, usually they didn't live in the socioeconomically deprived areas. And in general, they were less likely to be obese, smoking, drinking alcohol, or reporting health conditions. So also, this is another example of bias in the data also in healthcare. Another example is in large language models. This is about the anti-Muslim bias. And this was using GPT-3, and then they tried 100 times the phrase, "two Muslims walked into," like the autocomplete. And then they fell down to that 66 times. The system completed with words like shooting, killing, and others. And when they were using other religions, the number was lower. So how we could avoid this? What was the problem that happened with this algorithm? So as I told, there is no single problem, no single solution. And for example, in the Compass, they have a problem in the data ingestion. So they didn't balance the system considering that minority populations were the populations that were mostly arrested. And in the UK Biobank, they have a selection bias. So they have a kind of health volunteer, but they were volunteering people with the same characteristics. So this is kind of another type of a selection bias. And in the religion areas, to reduce bias, they would need to introduce more positive associations because they have more negative associations towards some religion groups. Another method, when we are using data sets, and this is proposed by one Google colleague that was from Google, the Timit Guru, and she proposed in this work that we should document the data sets, but giving more specific characteristics related to bias, such as the collection process, mitigation of severe consequences, and during the pre-processing and cleaning, understand the distribution of the data. Another one is for the NLP statement. So you should have more details, such as the speaker demographic, language variety, speech situation, text characteristics, and other important information. So you could populate your system with more diversity. The NLP data statement, this author proposed that this is similar to other fields. So psychology and medicine, they also need to standardize information. So it's not something, a specific need from machine learning field. Other fields also do that. Electronic industry also have their parts documented, describing how to use. So we could do something similar for machine learning as well. So conclusions. My goal here was to show the importance to identify and mitigate bias in machine learning algorithms. And I tried to present some practical guidance and how ML algorithms could handle bias and discrimination. I presented some examples of issues found in some areas, but these are just some examples. We could have more other areas also suffering with bias. And then I explained here some minimal principles for ethics and fairness. And my objective here is that when we are developing algorithms, you could support human values, and you could be better prepared to identify strengths, but also weakness of our systems, and keeping tracking and monitoring algorithms improvements over time. And then I'd like to thank all the support I have received here in ITA during my research. So from the Ecosistema Company, the Fundação Casimiro Montenegro Filho, CAPES, that I was a CAPES scholarship before, and also to my company at the moment, the Grupo Boticário and GAVP, for the authorization to participate here, and the SLEDge ITA for the invitation. Thank you so much. Questions?
I know that it's not the purpose of your work, but do you know if there is an advance in the legislation on this kind of wrong kind of bias?
Yes. I would say, and this is the part of the presentation I will be doing at the University of São Paulo, so I did some studies. I can send you also, because it will be very good seminar as well. In Brazil, they have the PWEL, the law, the emenda de lei that they submitted now, describing some important parts related to the artificial intelligence, and they are focused also in not impacting population. This is in Brazil. Europe, I would say they are more advanced than other areas, so most of the AI ethics frameworks are in the North Hemisphere, except in Australia. Australia also, for some time ago, are doing some studies related to the ethics. Now, in the South Hemisphere, Latin America, we have good people. We have a lot of people developing knowledge in artificial intelligence. So we also need to start to discuss about these impacts of algorithms. So Latin America also is moving ahead, but I would say the European community is the one that is driving some discussions. And in US as well, they are companies like Google, Microsoft, they are discussing much more about the impacts of the Facebook. So we have seen some news recently about these companies. So US is also driving strong tasks related to ethics. But in Brazil, we have o marco, né, da inteligência, the marco da internet, and also this emenda de lei, specifically for artificial intelligence. Okay. Yes?
You mentioned that in fields like medicine, for instance, there's already some kind of care about the way data is collected to avoid bias. Thank you. About how data is collected to avoid bias, because there's a need of the application to be unbiased for certain kind of studies. But when you talk about machine learning at large, as it is today, we are talking about data that's not properly controlled, right? So you don't have a proper questionnaire that's prepared, for instance, when you collect data for clinical studies on medicine and so forth. So here's a little provocation. Do you think that because of this lack of structure in data, at the end of the day, you are going to need machine learning to reduce bias?
That's really a tricky question. What I've been learning is that machine learning is helping us at least to notice that there is a bias. But I think bias is more related to we as a human being. During the decision-making process, we have the mindset that the algorithm could be doing something that could be harmful. So I believe more that this is driven by we as a human beings than from the algorithm itself. The algorithm itself, for me, and this is really a personal opinion, is a tool. The algorithm will do what we tell the algorithm to do. And then this is why I believe much more in the mindset than the algorithm. But on the other hand, what I have seen, I saw in one seminar from IEEE in bioinformatics, where they also presented some cases of bias in medicine, for example, in derma studies. So we have different colors of skin, and how this impacted the machine learning when they are studying, for example, cancer in the skin. So there are also some studies about that, how we can improve the algorithms. But I believe it's our responsibility to make sure the algorithm is operating well.
Okay, thank you.
Okay, thank you.
Thank you.
Okay.
Thank you, Daniela.
Thank you.
Thank you. With Daniela's presentation, we'll end the morning session, and we are going to have a lunch break now. And we are starting the afternoon session at 1:20, and we are going to have two sessions, in fact, during the afternoon. The first session starts at 1:20 and goes to 2:40. Then we are going to have a coffee break. Then we have two more studies to be presented, and then we are going to have our keynote speaker, Maria Fazli, giving her presentation
entitled The Potentials and Perils of Data Science and AI. So, I believe more that this is driven by we as a human being. During the decision-making process, we have different colors of skin, and how this impacted the machine learning when they are studying, for example, cancer in the skin. So there are also some studies about that, how we can improve the algorithms. But I believe
Thank you very much. I hope you can find a restaurant. There are restaurants around here. You can ask me later, and I see you 1:20. Thank you.
So the next presentation is a multi-criteria decision trading system based on prospect theory, a risk-return analysis of the TODIM method, presented by Bruna Puppo. So Bruna, you can start your presentation.
Hi everyone, good evening. Tá ligado? Tá, né? Hi, my name is Bruna, and today I'm going to present our paperwork, a multi-criterion decision trading system based on the prospect theory, a risk-return analysis of the TODIM method. The authors are me, Dr. Elteris Bruzi, Dr. Michel Lelis, and Dr. Leonardo Moselli. Okay, when you talk about the stock markets, most people thinking something like that. But with the improvement of technology, we go from this to this. And today we have different tools, different ways, and 1,000 of methods to analyze the stock markets to help the trader to make his choice. One of these tools is called trading systems. The trading systems are tools to operate in the financial market. They have predefining parameters that can be in several ways. We can make analysis, fundamentalist analysis of the company. In our paper, we are using the technical trading rules. And then they give you signals for buy and sell stocks for the trader. But at the same time, that technology provides us a new set of solutions. The amount of information that we have to work, tools for trading, and fancy techniques that appear every day give us a lot of questions. Like, which one's the best to choose? If I look for profit, I use the same tool, or if I'm risk-averse person, I use the same way? How people make their choice? Okay, to think about it, we start with the idea of traditional finances that believes that every decision is rational and that the market is perfect. But we know in the real life it's not like that. So the behavioral finance came to reduce the gap between the traditional finances and psychology and help us to understand how people make their decision-making process of real people in real world. Based on this, two psychiatrists develop a model, the prospect theory, that aims to understand how people make their choice in face of two different situations, earning and risks. This theory is based on the principle that people behave differently when you talk about gain and loss. In one way, people are risk-averse to gain, but they are risk-seeking for loss. And they are much more sensitive to loss than to gain. As you can see here, the joy that I have when I win $10 is less than the pain that I have if I lost $10. Okay, we know now a little more about how people think, how people make their decisions. But how can I use this to help them to make a choice? We have a set of techniques. One of them is called Multicriteria Decision Aid, or MCDA. It's a part of the operational research that seeks to select the optimal or the best set of the best set of alternatives from a finite set of solutions, taking in account many attributes or criteria and many goals. Okay, based on the prospect theory, the TODIM method was developed by Gomes, a Brazilian, in 1992, and seeks to quantify the alternative considering three different situations: gain, losses, and difference. To calculate to evaluating his global value, they considering an attenuation factor called theta. When you have losses, this losses is highlighted by this factor. It's a way to mathematically base it on the real behavior of people. Okay, here you have the algorithm that you use. Use the software MATLAB to application the method. As you can see, we have a set of alternatives. Here we call A. What is this? It's what I have to choose. I have a set of options, and I have to choose 1, 2, or 3. This is what I have to choose. Okay, but how can I choose this? We have the C. The criteria is how I evaluating this A, this alternative. In the end of the process, I have the ranking of the alternatives according to the global value. Okay, let's go to our proposed approach. Our proposed approach is to select a trading system that I told earlier among a pool of options using the TODIM method. And then we're going to make a backtest with TODIM TS, that is our method, against an ensemble TS developed by Lelis. It's published in ITA System Journal, and we compare the results. Okay, our work using the column work for method. What it means? It means I have a training database, then I'm applying the process, and have here I have my training data. I apply the process and have the results. These results are incorporated again in a new data set of training, and then I have the results. They are incorporating the new data training, and I keep doing this. Okay, what's our data set? Our data set is a series of daily prices of Brazilian stocks market from the period of 2002 to 2007. Okay, here we have the 18 stocks that we use. To choose them, we have a list of restrictions, okay, but it's more detailed in the article. It's meant to talk here. And then we need to set our alternatives. That is our technical trading rules. To make them, we use the following parameters, and the combinations of them give us 270 rules, or 207 alternatives. Okay, to evaluating our alternatives, we use the training database, then we simulate each one of the TTRs, as you can see here, 1 to 2017, and then we're evaluating them using 18 metrics. As you can see, we have índice Sharp, índice Omega, índice Kalmar, profit, expected, and then we apply our two methods, the TODIM that we are using, and the ensemble that is our compare method. As you can see, both of them start with the same matrix, but one, because of his process, gives one option, and our TODIM gives her another option. Okay, now what we can do? Calm down, I'm going to explain. Will be easier. Then what we do? We compare the results of the TODIM TS. We apply, again, the stock, just using the TTR 58, que is the ensemble, and the TODIM TS, that's here. And we have these results. Let's explain a little easy. Here we have just 3 of the stocks. Here we have 8, and we have 3 time series. Let's keep it simple. We have 1 time series. And to compare, we use 3 different metrics. The first 4 metrics are risk-based. What's the risk of investing my money in these stocks? And as you can see, the results where TODIM is better are highlighted. So our method provides less risk than the ensemble. The second set of parameters are risk-adjusted metrics. That's considering the profit by a risk. As you can see, our method had the best results. The last one are, oh, sorry. Here is profit adjust. It's wrong here, sorry. Here is just the return, okay? Here we have a little more easy to understand. We can see our method are better in almost 72% of the scenarios, considering risk, 65 considering risk adjusted, and 74 considering profit based. Okay, as you can see, our method could give us the same level of return with less risk exposure. And what is this? If I have two trading strategies provide the similar return and a strategy that exposes the invested capital to lower risk is preferable. Our method outperformed in almost 7% the scenarios, the ensemble. The results corroborate the idea that IMCDA based on, in the prospect theory, as TODIM, can reflect in decisions with greater risk aversion. Well, TODIM TS, it's a tool, a general and adaptive tool to support the trading strategies, has superior performance considering the risk metrics, and for future works, we are seeking to investigate a method to select the parameters in an optimization way, to propose the decision-making process, and to consider improved TTRs. Oh, thank you. Is this?
Thank you, Bruna. Are there any questions? Okay, Maria.
Quick one. You can hear me, right?
Before the transmission.
Okay. So can I ask you, the data set that you're using, you said daily prices. Is this opening and closing prices or tick-by-tick data? For the whole day in the 8 stocks that you're considering? Thank you.
Any more questions? Okay, let's thank Bruna again. So the next presentation, let me see here, is the influence of deep reinforcement learning algorithms in autonomous trading and cryptocurrency market by Gustavo Fonseca.
Everyone can hear me? Yeah.
Go ahead.
Thank you.
Oh, sorry.
My bad. Thank you. Thank you very much. My name is Gustavo, and today I'm going to give you a short presentation on the influence of deep reinforcement learning algorithms in autonomous trading in cryptocurrency market. So, my supervisor is Professor Paulo André. And before we start, I'm going to give you a short summary of my presentation. So first, I'll talk about a little bit about autonomous trading context. And after that, I'll cover a short description about cryptocurrency market. We'll have a little or a simple volatility in comparisons between 3 types of markets. And next, next, we'll have a short application of machine learning in trading context. And finally, I'm going to propose my research on deep reinforcement learning applied to quantitative finance. So what's it about autonomous trading context? It's also known as a black box trading tool, where formulas, rules, or statistical estimates are given to interpret or generate trading signals. So in this picture, I can present a simple framework regarding autonomous trading, and it's composed by 3 pillars. The first pillar covers the market data thing. The second one is the trading decision, where trading signals are generated. And in the last pillar, we use a multi-asset platform or API to perform orders management. Sorry, should I continue? Yeah. So in the market data pillar, we have everything related to stocks or some instrument data. So it's used as an input data, like fundamentals or historical prices, orders book, volumes, news, or even social media sentiment. So having this data, one can use a set of analysis such as technical or quantitative analysis. In technical analysis, one can use candlestick patterns, price action, movements, or indicators. But in quantitative analysis side, one can detect some displacements with more than one pair or more than one stock, correlated or co-integrated, and decide to trade with them. Or more classically, people use pricing models like Black-Scholes, Brownian movement, Monte Carlo, or even machine learning techniques to predict price. So having a trading signal in the third part, it's just to use a multi-asset platform like Bloomberg, MetaTrader, and so on to perform orders, buy and sell orders, cancel, reject, and adjust positions. So why cryptocurrency? Well, its market cap is about $1.7 trillion, and it's one of the most accessible financial markets when it comes to retail traders, where peer-to-peer transactions happens every time. And one another interesting thing about cryptocurrency is about volatility. So in this slide, I present a simple volatility analysis comparing three types of markets. The Bitcoin representing the crypto market, IBOV, which is the Brazilian stock index, and Euro USD, which is the most traded forex pair. So as you can see in this table, the Bitcoin return variances is the highest one. So if we have high volatility, we have high trading opportunities. So here's an example to combine machine learning in trading in a volatility trading scenario. So in this use case, I used a random forest ensemble to predict GBP oil price, having this following trading signal represented by this circle. So when the closing prices are below or high the Bollinger Band, there is a trading signal. So the algorithm will predict only if this condition is satisfied. Otherwise, it won't predict anything. So the idea is to produce features of the last, let's say, 20 or 40 periods of candlesticks, patterns, Bollinger Bands, or indicators like relative strength index, and all of them are normalized. And I need to point out that the relative strength index is already normalized. So the idea is to compare two approaches of the same trading signal. The first one is the baseline approach. The second one is the random forest approach. In the first approach, the algorithm will trade always when the condition is satisfied, and with fixed stop loss and take profit prices. On the other side, the random forest approach will predict always when the condition is satisfied. But besides, it will trade only if the delta price predict is above a threshold, a user-defined threshold, or otherwise it won't trade. So it uses as well fixed stop loss prices, but variable take profit values. And the variable prices, take profit price, are given by the random forest predictions. So in this slide, I backtest both the strategies or the setups, and here are the results. The baseline approach produced a minus 455% return, while the random forest approach produced a plus 86% return with the same trading signal. So another difference is that the random forest approach traded only 3,500 times, while the baseline approach traded 25,500 times. So the conclusion is the random forest could detect or filter the more promising trades and profit with them. Another thing to point out is that the random forest approach should be testing real trading conditions. It's only backtest, so maybe we'll have some problems here. So what are the next steps? The next steps is to introduce deep reinforcement learning in this context, in trading context. And deep reinforcement learning is a combination between deep learning or neural net with reinforcement learning algorithms. So how can we profit from volatility opportunities in cryptocurrency markets? That's the idea. And like Prado said, the rate of failure in quantitative finance is high, particularly so in financial ML. So here I present the research roadmap. First of all, I will start to study the state-of-the-art of machine learning techniques when it comes to autonomous trading. After that, I'll have a look at cryptocurrency-enabled technologies, blockchain, and distributed ledger technologies. And after that, I'll have a deep dive in deep reinforcement learning techniques. And after all the research is done, I will develop an end-to-end trading system, having both backtest and live trading platforms, using different types of libraries and APIs like Binance API and so on. So after that, we'll plug in some DRL architectures into an existing crypto portfolio trading system and see if we have improvements in results or not. And finally, the whole infrastructure will be available as an open source code in order to other researchers could contribute to my research. Here are some references. And thank you very much. I'm glad to be here.
Thank you, Gustavo. Are there any questions? Just a second.
Gustavo, I saw that you used p-normalized as feature. It was a feature. Yeah. So this p-normalized was p minus the moving average. Yes. There wasn't a normalization because this distribution can change a lot over time as long as the price increases. Yeah, that's true. I decided to. Sorry. There are more questions.
Yeah. That's true. I decided to calculate only the spread. So in this context, we'll have always the spread price minus mean minus average and everything minus average. So we'll have a spread distribution. And I took a look at the distribution and they were fine, and I decided not to normalize with mean. But it was just a simple use case. I don't know if I took the best practices in this simulation. I just used kind of a feeling and had a look with the distribution.
The reason why I ask that is because if the price is, goes by multiplied by 3 over time, like a difference, a spread of a unit 1 is It's very different of a change of unit 1 in the future. I don't know. Okay, but you explained that well.
Will increase. That's what
naturally increase, and the distribution over time. That is an issue when working with quantities is really present there. But okay, I have another question. Is that the baseline that you used was so bad that you could just make the opposite of it? And
can you repeat that? I couldn't understand.
Okay, the baseline that you used was really, really bad. And I keep asking myself, why don't you just take the opposite of that baseline? Would be
just to compare, but the baseline approach, yes, is really bad, and it trades all of the time. So when forex markets are, chopped, they are trading and losing money every time. But yeah, it was a decision to not filter the signal, to use a raw signal, and to improve the signal with an approach. In this case, a machine learning approach, but in other case, you can combine some indicators or some market scenarios to, filter a little bit more.
In this case, the machine learning method was just to filter and adapt the take profit. It was just for it. Okay, now I understand. Thank you. And the last question is about the universe that you used. It was just one currency, or was it?
It was just for GBP all, if I'm wrong. But yeah, I nowadays have a trading system that trades in about 4 forex pairs, and use these techniques. Of course, it's a little bit different, but this idea is using to trade and validate my system.
Okay, thank you, Gustavo.
Thank you.
Congrats.
So let's thank Gustavo again. The next presentation is Deep Learning for Financial Time Series Modeling by Atilius Brana.
Não acredito que não vai reconhecer. Tá. Deixa eu ver se... Acabei de fazer isso. Ele não está sendo lido por um motivo. É um workshop. Sou eu agora? Você pode ir? Posso. É apresentação workshop. Apresentação. Aí, não. Posso colocar?
É a última versão. Aí, 64.
So while we wait for the presentation of Atilio, we are going to move to our next presentation, is Data-Driven Intelligent Manufacturing Decision by Paulo Vitor Freitas Lopes. So, Paulo Vitor, you can go ahead.
Thank you. Oh, okay. Hello, good afternoon. I am here today to present my research until now in my doctoral degree. Until now, I am from another area, and I entered in the doctoral in a project of intelligent manufacturing systems. So I used all disciplines to understand the field. So here I will present my advances and my research results in order of the papers that we have written. All these papers were written with aid of professors and another students. So, first paper is structuring the problem of implementing technologies 4.0 in a hygiene industry through a methodology of soft operational research. Paper 2 is a paper about complex networks and simulation of manufacturing systems, and paper 3 is a predictive monitor for intelligent welding systems applied to Industry 4.0. So further works are my PhD thesis and what I plan to do. First of all, this is a fluxogram that exposes all the fields that were passed until now. First of all, I didn't understand how manufacturing systems could become intelligent. So I understood this through the application of soft operational research and trying to understand in the manufacturing and industry system how could they improve the manufacturing, production, organizational, and product areas to try become a framework of Industry 4.0. After this, we needed to simulate and try to have database of these throughputs, so we could study this by data-driven analysis. Hello. At the end of these studies, we have forecasting and diagnosis, forecastings and identification task in a welding system. So we could literally monitor this system. So we passed through all these phases until now, and the mapping was well done. The first paper that was about software operational research counted on the help of these authors, Roberto Douglas, Fernanda Vilela, and Carmen Belderrame, that was the professor here. And the motivation was the process of change in order to improve the quality of production chain. And this work addresses this issue by applying problem structuring methods to guide the implementation of technologies in the context of Industry 4.0. So we applied and developed this framework, or this multi-methodology framework, to organize all that industry and tried to propose a plan that they could utilize for improve their industry and manufacturing systems. So at the start, we interviewed the stakeholders. So we carry out mapping interview with sorry. So we mapped their interest and potential processes, and you applied value-focused thinking with objective definition and a generic action plan for technological innovation 4.0 in relevant systems. Here, we had a document of many pages, and we had to filter all this information. To filter this information, we applied the second step, that's here in Portuguese, the second step of soft systems methodology. And we applied a questionnaire to address the evolution stage diagnosis of that manufacturing system. So we identified the real situation and identified the distance between the real situation and the situation of interest. So we could develop the human behavioral systems and identify what changes were capable and what changes were desirable. With the application of EFT, we proposed a generic action plan, and through the SSM methodology, the relevant systems were identified. So we observed a great opportunity of improvement, the production chain, and the organizational sector of the industry in question. There were 4 systems that were evaluated: production, technology, organizational, and manufacturing. So after all of this, the systems that we found that were capable and desirable to be changed was the production chain and organizational. If you are interested, we can talk about this later. So the second paper was about simulation in manufacturing systems, and here I have to thank to Roberto Douglas, Felipe Verri, and Leonardo, that they were a very special piece of this, and I am just another that have participated of this project. They are the brain upon this. We have manufacturing systems that have a wide range of elements and infinite processes. These relationships constitute the complex manufacturing networks. Therefore, techniques and complex networks are also very good tools for dealing with complicated relationships on the production line. However, collecting manufacturing data is very difficult. There is various privacy issues. And we tried to simulate this, to have this data, and after running some machine learning and artificial intelligence and validate these models. So the following question is considered in order to guide this work. Is there a fundamental network model that can mimic the work of real-world manufacturing system, and what is the dynamic behavior like? This is the question that wrote our work. So the main objective of this study is to assess the global static and dynamic behavior of this complex network model that represents a manufacturing system that grow almost randomly. This conception of a flexible model for the generation of networks, the main objective is divided in 3 specific objectives. First objective, the conception of the flexible model of manufacturing systems. The second is the development of a throughput simulation, and after all, analysis of this dynamic behavior. So we proposed the manufacturing network random model that we called MNRM, that generate the networks based on the number of machines and the number of production steps. And other characteristics are the production rate of nodes, failure rate, and the buffer size. Complex manufacturing throughput simulation that Flip called clematis. Every simulator capable of emulating the production process of a factory floor, and during the production, every node in the system can be in 3 states. There are starved, blocked, and working. And in each iteration of the production process, the nodes state and the amount of material in their buffer are updated. So here are some figures that Leonardo has done to us. Okay. So here is an example of the manufacturing system, and here is an example of the clematis running. The time is, we are out of time, so I will faster. The important thing about this is that there is a phase transition where it starts, where the alpha parameter is the production steps per machines, and when values are bigger than 0.2, the more linear that the manufacturing system is, better. But if alpha is lower than 0.2, more parallel that the system is better. So this behavior can be explained using the concept of throughput bottleneck. And here is a keyword, throughput bottleneck. So paper 3 is predictive monitoring for intelligent welding systems, machine learning applied to Industry 4.0. And the authors are here. The proposal is building a predictive monitoring system used on industrial welding process to guarantee the quality of the welding. So knowledge of welding process are largely developed empirically, such as trial and error, destructive experiments, or experts' knowledge. Consequently, there is an effort to transference of the human intelligent attributes to intelligent welding systems. That is what we studied. Here is the fluxogram that represents the dataset pre-processing that this data was collected from a real factory of Tenaris in Canada, and we had to pre-process the data. And the machine learning framework. So we are 50 seconds, so I will pass through this. The model, the dense model, no. We tried to do some yeah, I will not be capable to explain this so fast. So I will pass through this and explain the next part. That is the further work. That is the throughput bottleneck analysis in manufacturing system with the aid of artificial intelligence. That is what I'm trying to do now and my further works. The machine called throughput bottlenecks emerged in manufacturing systems, and it was studied by analytical and simulation methods. Can I get 2 more minutes? 1 minute? Okay. Mainly applying analytical and simulation methods. But these methods, analytical and simulation, are very difficult to handle in manufacturing floor, in shop floor. So we are trying to apply intelligent, data-driven strategies for throughput bottlenecks, and not only identify these throughput bottlenecks, but identify, diagnose, predict, and prescribe in a manufacturing system. So I thank you all for the attention, and I apologize about my time issues.
Thank you, Paulo. We can ask many questions afterwards. That's why we have coffee break, okay? Are there any questions? We have time for one question, maybe. Okay, Maria?
Thank you. Can I check when you will be doing the majority of your own research work? As part of looking at throughput bottlenecks, will you be looking at the problems that arise when essentially manufacturers get orders, but they require modifications in the line of production? So the simplest example to give is, imagine that you are manufacturing Porsche cars, and your standard model is a red model, and there's an order for silver Porsche cars, which means something needs to change in the production line to change the paint, but that introduces delays. So will you be looking at these kind of problems?
No. The changes in manufacturing systems are constant. They are not static. So we are studying the throughput bottlenecks that can be caused by any cause. So to start this, we first need to identify our bottlenecks. Our bottlenecks identified can be, as you said, a bottleneck caused by the changing of this framework of the manufacturing systems, or the bottleneck can have another causes. The causes of the bottlenecks are studied in the diagnostics phase. After the diagnostic phases that requires a great understanding of the context and the constraints of that manufacturing systems, we start to try to do monitoring, predictive monitoring, like we have done in the welding system that we have monitored. For further work is the prognosis, is forecasting this, and after the forecasting, try to avoid these manufacturing throughput bottlenecks, and trying to avoid this throughput forecasted, we have the prognosis. So we have 4 different stages, and each stage has its own particularities. Thank you, Professor, and thank you all for the attention.
So let's thank him again. So we are going. So going back to the next presentation, that now we have here. is Atilio Isbrana with the work entitled Deep Learning for Financial Time Series Modeling.
I'm back. I think this time is going to work out. Okay, so I'm Atilio, and I'm a PhD candidate here, supervised by Professor Paul André. And my research is on deep learning for financial time series forecasting. That's what the title says. The univariate forecasting problem is a fairly interesting problem for artificial intelligence in general, because it's really at the core of what intelligent decision making is about. It's about having agents who work in an environment and try to predict what their actions will result in based on their cost function. So this really is at the core of when we try to do something regarding artificial intelligence. All right. So in terms of objective, so what is the objective of forecasting a univariate time series? It's about looking at past states of any given signal, model what is the data generation process behind it, and finally predicting the next few states, which is basically what we do all the time. We try to predict what will happen in the future, so we try to act based on that prediction. There's a distinction between univariate and multivariate, and one of the reasons why I keep this research mostly focused on univariate is because it's a more standardized approach, where if you go into multivariate training and model comparison for multivariate, it's possible, and it's quite easy to get univariate models to become multivariate, but it's easier to test models on just a plain range of univariate time series in terms of how well they can really grasp the data generation process behind it. The most traditional approach, and one of the most traditional approaches that we have, is signal decomposition. I have an exhaustive list. There are several, lots of research papers for decades already on that were built in things like this, which is the famous ESL, which you get error ETS or ESL, it doesn't matter. Error, trend, and seasonality. You get like a signal. You get some of the parts which are says seasonalities about it. You get some parts that you may have a trend related to it, and you get some error, which is a fairly useful. It has been fairly useful as a kind of heuristic approach to trying to come up with what is the data generation process behind a series. And in this work, I focus on financial time series, which are pretty complex. The financial system is a very complex system, and it's made of several complex systems that are underneath it, which are basically human trading, human brain, and the human species in general. So it's a fairly complex system in terms of modeling emergence and so on and so forth. What are the rules about it, of the data generation process there? So okay, so historically, just have a brief historical perspective on this. Statistics was mostly what tackled this problem of forecasting. Was basically since a few decades ago, since the I guess 40s, 50s, and 60s, and so on. And most of the traditional methods for approaching it are the Holt-Winters, which is very related to the error, trend, and seasonality that I showed, and things like Box-Jenkins and autoregression, which are more related to ARIMA. And then people used to like to compare each methods, and try to, and they were very aggressive with each other in terms of cursing and so on, because there was what is the best data generation modeling approach for the data generation process of a time series. Theta was one of the better methods for a long time, which was a simple average of linear regression and exponential smoothing. So that's what we had. And then about in the 70s, Makridakis, which is a professor at the Nicosia University in Greece, he came up with the forecasting competitions to really settle the dispute that they had, the academic dispute, which started to have kind of a competition between Holt-Winters, kind of exponential smoothing researchers and ARIMA ones, up until and then in that environment, in those competitions from 79, 93, and 98, there was virtually no machine learning, or any machine learning that was tried to approach this failed, basically. And then in 2018 and 2020, we got a different thing, especially because of the recent boom of deep learning of the past decade. So machine learning introduced something that is very different, which incorporates an approach of meta learning already, which is basically trying to not build models that are for each time series and have local models, but instead have something that would learn how to model. Basically substitute the whole process that we use in exponential smoothing or ARIMA into a global model that will model any time series. And but still, until 1998, machine learning univariate performance was worse than naive. It was actually worse than predicting that the last step is the next step. And we got some evidence that recurrent neural networks were good in multivariate settings, but that was kind of it. So in the M4 competition, which is in 2018, things got different, but just because of one submission. So the meta-analysis of that competition was that the best model was a hybrid model from exponential smoothing and LSTMs, basically. And it was 8.6% better than the benchmark. The second, which was a mix of machine learning and statistical, which is decision trees and some statistical models, was actually a decision tree model to select statistical models, was good. It was 6.7%. And then these statistical models, the traditional ones, didn't do really well. So that's where things started to shift in the direction of having machine learning as a better forecasting model. And then, highly provoked by the conclusions of the statisticians of this competition that still thought that building hybrid models and building models with machine learning was the way to go, they proposed a pure deep learning approach by some folks at Element AI, which is the company from Joshua Bengio in Canada. And they introduced no a priori modeling, which basically doesn't include any prior knowledge of statistical decomposition or statistical properties of distribution and so on. And it's just a strong decomposition method that I'll show. And this is kind of where I'm going to get. This is a quote that is quite famous. And I don't want to get too into the deeds of this. But every time I fire a linguist, the performance of the speech recognizer goes up. It's a very famous quote from Frederick Jelinek, which was the former IBM researcher and head of the Center of Language and Speech Processing at Johns Hopkins University, which is quite a telling thing. When you start working with purely machine learning models, my prediction, or the prediction of a lot of research, is that it should probably not. You should probably stick to not incorporating human knowledge in it. Although there's a lot of people who really defend the opposite of this. But part of this research is trying to prove kind of this point. You don't need to incorporate a lot of traditional statistical knowledge into forecasting models. And so we're now, this is the background, and the toolkit up until the M4 competition was statistical methods, deep learning, and recurrent neural networks, and then that's where this research starts, which is basically, okay, how can we get better? Well, time has passed, almost 3 years have passed, and we have general deep learning improvements, which I'll go quickly through. That's the lazy approach, just incorporate what the other things that the literature have been recommending. The other thing is to get like inspiration in analogous fields such as natural language processing, because natural language processing is also a sequential problem, and you can derive you can try to extrapolate that they will work really well in another sequential problem, which is just a time series, a signal processing. Just should be even simpler than embedding meanings and so on and so forth. So, and that's what we've got is attention and transformers. You probably have heard of GPT-3, GPT-2, and so on and so forth. I'll go briefly towards it. Now we have the perceiver now, which is proposed by DeepMind a couple months ago. So that is probably a very good way to go in terms of deep learning for time series forecasting. And then you finally have neuroarchitecture search, which is also a field that can really improve architecture, basically. And it's been really highly researched in the last few years. Okay, so why do we Why do we use deep learning? Well, the best model that we have today for deep learning for time series is actually called NBeats, which was that one from Element AI. I've proposed already and published a paper that includes some transformations, including putting recurrent neural networks in it, and using new architecture search for improving this model. And that is one way to go. The benefit is of this model. It's a really simple and intuitive model. You have 4 layers of multi-layer perceptions, which try to model the first layer of data of the decomposition, and then pass the input that they got minus what they understood about this data to the next layer, which is a 4-layer multi-layer perception can model a lot of polynomials. So it basically he's trying to do with 4 layers, trying to model the first data that they see, the first pattern that they see, and pass on what they learned into the next one, extracting that from it. So it's basically using really residuals. It's like, what I don't understand, you take it from here. And then this block, which is just a 4-layer multi-layer perception, just does that up until 30 blocks. And you have good gradient descent properties here because you're using residuals. So you're preserving the input, and you add up the forecast. So that's it's good. It's purely learned. There's no a priori knowledge in this. No pre-processing. You actually don't have to do any pre-processing. You can just throw the numbers in there. You don't have to min-max or do any standard, which is a great goal, in my opinion. There's no normalization. The residuals counter any problems with vanishing gradients, which is one of the great technologies that we have is residuals in neural networks. And you can work with any type of data. Actually, we use this model to solve NP-complete problems, small NP-complete problems in games, in single-player games. Some cons. It's an expensive training because it doesn't, if you add to the input, it scales polynomially. So it's not very interesting in terms of that, and requires assembling, which is quite expensive as well because you have to have several models and so on. So it's not so useful. Okay, so I'm going to go, and I only have 5 minutes, great. So neural net literature improvements. I will go through this. There is MISH. MISH came from a lot of research on searching for better activation functions, and that is the new thing that is better than ReLU. So that's a thing that we can just put into NBeats and go, and it does improve NBeats. It does improve gradient flow and so on. We can use better regularization of variance in the Atom optimizer. Basically, that is a Microsoft research paper, which does really good, does work really well consistently across, which is kind of a warm-up in the early updates of training. We have look-aheads, which was proposed by Geoffrey Hinton and the folks at Toronto University, which is a great optimizing trick to converge faster, basically. And these are all searched and found empirically. There is very little, it's basically all of this came up with people understanding there are some quirks in the training and trying to patch them. And that's basically all of these improvements. And just using better learning rate schedules as well. This is MISH, just out of curiosity. And this is the look ahead. You basically, instead of just updating into a new state, you give 5 steps and then average out your weights. It's very simple. All of them are very simple, but very powerful. The other thing we can do, we can use attention. Okay, I already talked about attention before, and you have now the perceiver, and then the perceiver is very powerful as a new DeepMind innovation. And the perceiver AO even better, which is a global attention mechanism you can apply to anything. You can apply to games, or you can apply to multi-level data. You can apply to vision and so on. And you obviously don't need domain-specific knowledge. You can use arbitrary size inputs and arbitrary size outputs, and scales linearly. And that's like the big thing about it right now, because you have a transformer-like thing that you can use very, very, very large models. It could even allow a lot of very multivariate, large-scale training. So that's really good, and that's what we're trying to implement. This is the smaller, more efficient transformer, basically. And then we finally have neural architecture search, the last topic, so I'll just go briefly through it. So this is related a lot with the carbon footprint problem that we had in in artificial intelligence, which this is my argument against this being a huge issue, because what happened in 2017 is that Google, with this research here, which is called reinforcement learning neural architecture search, came up with, let's use 800 GPUs for 28 days and find a new architecture. And they found a great architecture for the CFAR10, which is this one, with a groundbreaking 96.6335 accuracy score, using 51 years worth of GPU hours, which is insane, right? And then they saw the carbon footprint, and there's a lot of related stuff with this and they said, oh, this is terrible. If we start using this kind of approach, this would be really bad. But Google themselves quickly, they had a lot of very bad neural architecture search approaches. But then Google themselves came up with ENAS, which is a model that I use in my paper, which basically uses 10 hours instead of 51 years of GPU hours, and it gets a better score. It's just that because of one technique called weight sharing that I will go through just because it's fun really quickly, which is in traditional search, you know what's the problem with that? Is you have a design of what your architecture is, you start training and you throw away everything that you got. And that's terrible, because then you have to train the whole model again. What you can do is a very simple approach. You, instead of doing training and oops, what happened? Okay, instead of doing training and then throwing away, you can just recycle into your new training. And why would that work? Well, you know, if you trained bots to learn about something like using a hand in a simulation game or using wheels, you don't have to throw that away. You can just recycle that. And how do you do that? It's really simple. Instead, you get a very big grid of weights, which is your search space. And every architecture that you train is a subgraph of that great search space. So you can basically have these weights that are constantly being updated into tasks, and then every time you get a new instance, you train a subgraph of that. So you can keep the weights, and it works wonders. You can get like amazing results like this one, like these ones. Like now, which uses 7 hours only, which is a little bit funkier optimizer with 96%, and you get a sharp dart as well, and you get all of these because they're using weight sharing, okay? So there you go, there's your carbon footprint problem, because it's not gonna be an issue anymore. Hopefully we can continually find these kind of solutions. And then finally, what am I doing, basically? Trying to obviously further deep learning research specifically for time series, which is something that is mostly spent on vision and natural language processing, or gaming. Improving models by way of better learning, which is, we already know some things. Scaling better, probably using attention instead of four-layer, multi-layer perceptions. And searching and optimizing with neural architecture search. So applying tests, ablation studies, and something that, that's what we're doing, basically. And that is it. Thank you very much.
So thank you, Atilio. Are there any questions? Professor Elton?
Hi, Atilio. Well, great presentation, great idea for research. I'd like you to detail a little bit more about the matrix competition, the results that you have showed there, that numbers. Could you detail a little bit more?
Of course. I think the competition, how do I go back? The competition was an open competition that there was a prize. It's kind of like always like 15,000 euros or something like that. And it basically includes every major research group. And it was mostly from the Journal of, International Journal of Forecasting that was organizing it. And so what they had was, okay, we have the traditional approaches and they had the benchmarks. So they said ARIMA and ETS are the benchmarks, and they have their own performance. You have a naive performance that it's even worse than this, which is basically if next month's sales are next month is January, let's just use last January's data to predict the next one. So that's a naive approach. We have a pure machine learning model here, which performed very poorly because it was a convolutional neural network that wasn't really fitted to this competition. And then you have these benchmarks. The theta benchmark was the benchmark of the competition because it was the last competition's winner. So that's why they used it, which is basically averaging ESL with linear regression, which is a very, very simplistic approach for it to use in any kind of series that you see in front of you. Then you have the statistical approach. I don't remember which one it was, but it was kind of an improved statistical approach. I don't remember which one. This was this was the Heinemann. He's a very famous researcher on forecasting, and he proposed decision trees with XGBoost, but selecting which are the models that it should use for each series. So it's a very out-of-the-box idea where you get a series and you just say, like, for this series, I will use an ensemble of statistical approaches, and that's chosen by the decision tree. Okay, and then finally you have the hybrid one, which was this fellow at Amazon. Is Smil. He's a Polish guy, and he proposed a decomposition method, and then after decomposing with ESL, he would get those decompositions like the trend, seasonality, and so on, pass through a recurrent neural network as a multivariate information input, and then have the recurrent neural network predict. And that was much better. The statistical approaches didn't have that much of a difference among them, right? From from theta to statistical, it was only 4.1%, and then they got much better. And then when the folks at Element AI came in with a pure deep learning model that didn't use any decomposition from ESL and so on, they got 11%. And this can be improved upon, honestly. I've already improved upon in my research a little bit, 0.3%, and you can after incorporating other things, you can improve even further. And the data set was 100,000 time series of random socioeconomic data of the world, like population in Africa, like, you know, economic, financial, and so on and so forth, industrial as well. So you had to just have, this is, you know, if you want a method, which one is the best one? Is it using ESL? Is it using EDIMA? Is this using some other kind of decision-making process among the statistical approach? And the winner was applied deep learning. That was the point of this whole thing, right? Okay, nice.
I do have a question as well. Sorry. Are there any other questions? Okay, so I can go ahead. So about your method, you told that you improved 0.3%?
Yeah.
Is there any disadvantage in your method?
Yeah, well, no, my method actually, it improved and it decreased the amount of models you had to include in the ensemble. So no, it was an improvement, but it wasn't as much of an improvement as I expected. There is one downside, which is the size of the network is bigger, so you need more RAM. Mm-hmm. But other than that, is an improvement. But recurrent neural networks are not, since the transformer kind of almost proved that recurrent neural networks are not as powerful as using attention, because attention doesn't give up information like recurrent neural networks does, because they use the input. It's a recurrent neural network that consistently uses the past information to create attention, right? So I would not use recurrent neural network. I think I got late in the game and I should have used attention instead of a recurrent neural network. So my idea now is to use attention into this as opposed to recurrent neural networks. Okay. Yes.
Great.
Yeah, no worries. Thanks.
So let's thank Attilio again. So with this presentation, we finish this session. In a few minutes, we are going to have a coffee break. Is that right, Professor Elton? In a few minutes? Okay, so 3:30, we go back? Okay, so this session is ended. So the coffee break is ready.
Great. Interessante. Desligou aqui?
Não.
Desliga.
Não sou eu que desligo.
Não funciona assim, não?
Let's continue the last session of the day. The third session, we're going to have the last of the presentation. And afterwards, we're going to have the keynote speaker, Professor Maria Fazli, who will give you a talk. Next, so I call on Dr. Emilia Colonese-Cahard to present her work entitled Big Data Models Benchmarking in the Context of the Anatel, the Brazilian Agency for Telecommunication, and ITA Cooperation Projects. Okay, I pass the word, Emilia.
Thank you. Can I have this?
Yes.
No, not this one. This one. Good afternoon. How? This is work from a student of mine, Bruno, but he could not present today, so I'm going to present it for him. And this work is about benchmarking big data models. In this project, we had this project like 3 years ago with Anatel. And it was made to create an analytical database modeling for a work project called PBLA. This is a project, it's a Projeto Banda Larga nas Escolas. It is basically to measure and to control the internet connection installation in all public schools of Brazil. Okay. And Anatel had no control of this installation, and they wanted to know how this installation was proceeding and how was the data that the providers were delivering to Anatel to control the data, and they asked for our help to do that. And we made this project. Was made in our laboratory, like big data science laboratory here at ITA. And the first thing we learned about the data was bad. Okay. The providers, they didn't inform their installations and the connection, the internet connection, quite right. Okay, this we discovered with the first project that was 2 years ago. And we informed those problems to Anatel, and they had to decide what to do, and probably they did. So we go on with the research. Once we create this huge database, we run the analysis that we wanted to run to check the data quality, and the test in database server took 10 hours to run. Okay, I said, okay, we have in this laboratory big data environment. Let's try to run the same test in this environment. So Bruno did this research. So what he did basically was to transform this snowflake model that was in a SQL server. Okay, this is basically the data for analysis that the data scientists get when they perform their analysis. And you know, guys, that your result will be as good as the data quality that you get, right? So we are worried about the quality, and now we are worried about the time that a machine learning can run and give us the result. So now we are focused on the time. First we focus on the data, now we focus on the time. So what he did is get this data warehouse model and adapt it to NoSQL database, a columnar NoSQL database, okay? That we use HBase. That's free and is part of a Hadoop ecosystem. So we decided to test 4 types of aggregation of these column families. First aggregation, we had the whole data, and we create one column family for everything but the time. We separate a column family for the time. The second one, we separate the column family for fact and time together. The third one, no, this is the third one. The second one was everything together. We didn't separate at all. Okay, everything was just like one family column. And the last one, we had each dimension and the fact separated all, each one in a column family. Okay, and we run to see if there was some difference and which were the best model that we could have as when we run the query that we want to run. So basically, we run the same queries that we ran at the database server, and the traditional one, we use SQL Server from Microsoft. So the first query that we run was a general query that retrieved all the coordinates, the geographic coordinates of the Brazilian schools. And we focus on the reports of December 2020. The second query, we divide in 3 queries that were very specific, and we added some filters and functions to check the behavior of the NoSQL database, how it will impact in our response time, okay? So the first query ran, we had like 91K rows, and the 4 models of HBase, we had little, I think it's little data. We could have more, but we wanted to know if there would be some difference. So we had some difference with the HBase model. And the model that fit best the query was when we joined time and fact together. So the response was better. Comparing the time, look at that. 91K with geographical data, designing a map, it took an average of 8 seconds in a database environment, while the same query, we try to replicate the same environment, the same amount of memory, the same amount of cores, okay? It took more than 10 hours in an SQL server. So this was very impactful for me because I didn't have seen yet until this day, what the big data could deliver us, what the environment could deliver us in terms of time. And we were running machine learning here, okay? We were running algorithm, geographic ones. So for the specific queries, we are dealing with less data, okay? And we add some functions, because we knew that when we add like joins and functions and run those queries in a big data environment, it has an impact in time. So, and that's what the result really showed us. We had, for each query, we had 3 queries. We selected 3 states and ran those queries against it. So the difference of time was not that big, okay? Because less data, SQL deal better, okay? The traditional environment deal better than the bigger data, but still, it took like more than 30 seconds against the big data that took less than 10 seconds. Even with little data and more refined and more difficult and more complex queries, the environment and big data did better, okay? And this is a very interesting result. This is 10 hours, 4 seconds. I was impacted. I didn't, I was not expecting this result. This is why the big data environment was adopted for those big techs, because they have a lot of data and they have to run Google, Facebook, and everything. This is because they adopted. This is the reason. So this is the result. The first query showed us a map with all the geographical location of the schools, the public schools, okay? And this took like 8 seconds to draw this picture, while in SQL Server, it took 10 hours. And the second query, the query was focused on finding the outliers of the internet speed. Because the providers, they said that they install one thing, and we really don't know if that is true or not. So we had to run some algorithms to see if what the data that they were reporting was true. And most of the answer related to those providers were not true. Even though we had these outliers, but I was not worried with the data quality, because this was addressed in the paper before. We were worried about the time, the execution time, the response time. And this took like 30 seconds in SQL Server and 8 seconds in big data environment. So what we conclude is that a big data approach brings a lot of benefits in terms of data retrieval time for complex data type. Also, the NoSQL models are highly dependent on the query complexity. Okay, more complex the query is, it takes more time to translate that complexity to a MapReduce framework that is beneath the whole environment of big data. The next one is that there is a little dependence on the number of columns selected in the query. So selections of attributes doesn't change much the time, okay? But filtering, it does. Not selecting, filtering. It's, I could say that feature selection doesn't impact, but reducing volume, yes, it does. The results of the general query, there was the one that showed the biggest difference. Benefits with the H-based storage, I mean, NoSQL. In this case, H-base was used because it can store like data warehouse models in it. Okay, and the models 3 and 4, one that used time with fact together, we create only one key for that, and the fourth that all dimensions and the fact are separated in column families, they run better than everything together. Well, this has a logic because when the column family is stored in an H-based environment, each column goes to one node. So when you query, all those data come in parallel, and the time is less for retrieval than if you have everything together. Okay. So we think for the future work, you could investigate more the impacts of defining column-specific partitioning of H-based tables and improve the design of row keys. This impacts a lot on retrieval data. So this is the work we did. This is a graduation work. Okay, it's just to show and be certain that the big data environment brings benefits to us as data scientists. Okay, thank you very much for your attention. Do you have any questions? Sorry.
Yes, I was up to asking if someone has any question. I have a question.
Oh, really? Really?
Yes. Please detail, just a provocation. I'd like you to detail a little bit more the big data cluster that we have in the laboratory of big data science.
Oh, okay.
How the work that you did there, that you built this one from the scratch, and today we have a good cluster on that laboratory.
We have 8 machines with 64 gigabytes of RAM memory, 24 cores. I think it's 3 or 4 gigahertz. I don't know. Certain. One is slave, 7 is one is master, 7 is slaves. But we had to restrict for this work the memories and the cores. To be fair with the SQL server, okay, try to be fair. The same amount that the SQL server, we restricted in our cluster, to have the same amount of memory, the same amount of core, okay, to try to be fair. Of course, it's not fair because it's parallel, but at least we try to replicate the same, at least the resource environment. Okay. So that was the result. Any more questions? No? Okay. Thank you. Thank you.
Thank you. Well, thank you, Emilia. And now we're going to have our keynote speaker, Professor Maria Fazli. But first, let me tell you that I know Maria Fazli about 8 years. It's already 8 years. And she gave me the first opportunity in my academic career. As soon as I have finished my PhD, she contracted me as a senior research fellow, which is a postdoctoral position in England. I know that we have many students here that one thing that you know for sure is that after your graduation, you have to look for a job. So everyone that gives you an opportunity is going to be very welcome. And so I would like to pay my gratitude to Professor Fazli et al. And Professor Maria Fazli is the Executive Dean of the Faculty of Science and Health of the University of Essex, which is a position similar to our head of division, I think, similar like that at ITA. And she is also the UNESCO chair in analytics and data science. And this position holds account with international support of ITA. In 2014, soon after I have left around that time, I remember that time that she was working on the foundation of the Institute for Analytics and Data Science at Essex, which is a so successful venture. But at that time, it was just a proposed venture, there was not the success that it has today. And in 2020, she was included in a list of a top 10 women leading the way on data science for her work. As I know Maria Fazli, she's a reference for my work, and I totally agree and more than support such inclusion. And I really hope and expect that you appreciate her talk, and I feel free to build a network, to listen, and to learn with her, like me have learned, and continue to learn along with my career. It's a great honor to call Maria Fazli for her talk. Thank you. Oh, you have to connect yourself. Okay.
Yes.
Oh, look. You remember?
The HDMI.
Yeah. Yeah, where to connect yourself.
Good afternoon, everyone. Thank you, Elton, for the very kind introduction. I feel that after that introduction, I'm not entirely sure I'm the right person to be giving this presentation. I didn't just give you the position, you were hired for it, and you competed like everyone else. So you should not be grateful to me. You earned that position, but I'm very pleased that it gave us the start of a collaboration. So you're grateful to me, but I'm also grateful to you, and I'm really grateful for this invitation to Paulo and Elton, as well as Professor Silveira, and welcoming me to ITA. This is really great to be here, especially after having had to postpone the trip 4 times because of the pandemic, and at some point it appeared as if it's not going to happen. But against all odds, here I am. So I think I'm the last talk for today. So there's a real risk I'm going to put you all to sleep. If you do fall asleep, just don't snore. I don't mind, just don't snore. There's a couple of points that I would like to make. I've been teaching for a very long time. I'm not going to tell you how long, because then you will be able to guess my age. But I still get very nervous when I talk in public. And there are 2 side effects of my nervousness. Side effect number 1 is I start talking really fast. So someone will have to indicate that I have done that. And you just do this, and I understand I'm going really fast. And the other one is I start walking up and down very fast. So again, someone will need to indicate so that I can stop doing that. So what I'm going to talk to you about today is the potential and the pitfalls for data science and AI. And we had a wonderful set of presentations earlier today that have actually set the scene for what I'm going to be talking to you. And because the audience was going to be quite varied, as we had discussed with Elton, Paulo and colleagues, this presentation is quite at a high level, and it's meant more to provoke you thinking. Some of you have already started thinking about the things that I will be talking about in terms of ethics, for instance, for AI and biases. But I'm just going to try and provoke you even more. So I'm going to start by giving you the context. So technologies, we have always, in our lifetime as a species, if you like, been inventing new technologies to make our lives easier. And these have had a massive impact when you look back at history. So for instance, we start with the agricultural revolution, and we came in communities. We moved from being hunter-gatherers into agricultural communities, and we've started actually shaping our landscape as a species in a very different way than we were able to do before. In more recent times, we have seen inventions like steam engines making a massive difference in the world, because they have been able to essentially shrink distances, and people have been able to travel from one part of the world to another, which nowadays may not be considered as a really big change. But at the time, you have to imagine people were stuck in their own little familiar places. They didn't have access to other cultures, so being able to visit other countries around the world would open up their minds. And this trend has just continued. So from trains that you would travel along with others, we moved to having our own individual cars that enable families to be moving around in their own way and visit relatives or visit other countries. And more recently, we've seen innovations such as television that have literally opened a new window to the world. Because suddenly you could be based in the UK and you could see what was happening in the Philippines or the US or in Brazil. And before, people didn't know about these other places that existed in the world. And of course, we have personal computers that have revolutionized our lives with the invention of the chip, and mobile phones that have completely changed the way we do things, from being able to communicate with each other to how actually we go about and we socialize. And we have social media applications changing how we connect with each other as a species. And perhaps this is where we're heading. And we were talking actually about this as part of lunch with some colleagues earlier today. Perhaps the next step would be a human kind of enhanced technology. We would have embedded processors or other prosthetic devices. This is already happening to some extent. It's just that we don't have these devices in our brains. So it could be that we are we modify our intelligence, we could amplify certain characteristics of ours, or we can even dampen down characteristics. So we have seen in the last few years, and these changes have been quite rapid. So this is a picture from St. Peter's Square in 2005. This is at the time when the new Pope was around, so everyone was waiting to find out who the new Pope was going to be. And if you look at this image, then you can see right at the bottom there on the right of the screen, there's someone holding a mobile phone that looks like one of these modern mobile phones with a nice screen. So this is 2005, and this device is transmitting data. So this is now 2013, and I think this picture is worth 1,000 words, because you can see the change within 8 years of how many people now are holding not just one perhaps, but multiple devices. And the point here is that these devices are transmitting data, they're generating data, and we as individuals are both producers and consumers of this data. And we are just not aware of how much we are consuming and producing on a daily basis. And all of this has generated a kind of almost like a landslide of technologies that have developed in the last few years, and quite a lot of hype, especially in the area of computer science that we are all working in, and some confusion and some perhaps anxiety about where it is that we are heading. So where we are is at a place where we have all of these processors, we have all of these devices producing data, and we are producing data as well. We have streams of data, and we've got the terminology of big data, if you like, as one of the kind of hypes that has been created as part of this. And big data means a lot of different things to a lot of people. You don't have big data if you can process things on your laptop. You have big data when you really need to go beyond what you've got within an individual department, and you have to use clusters and multiple GPU units, and you have to essentially create a completely different way to deal with the data to be able to say, I've got big data. The majority of companies, organizations that tell us, at least us in the UK, and when I talk to them as an individual academic and I try to see what it is that they are facing, they tell me they have big data, but actually when you look at the data sets that they've got, if it's in an Excel spreadsheet, it's not a big data set. So there's a bit of confusion here, because big data call for completely different, and we heard the earlier talk about, you cannot do it on an SQL server. You have to use a completely different structure for a database to be able to process such data. And then we have terminology such as analytics. And analytics, again, means all sorts of things to different people. And what I understand, what I mean when I use this terminology, is essentially different types of quantitative techniques that can range from statistics to data science and artificial intelligence techniques that enable you to process data and draw insights from data. But it's an all-encompassing term. And what has also emerged is almost like a new discipline. So we have computer science, we have mathematics, we have statistics, we've got other disciplines that have been around for a while. Computer science is relatively newer as a discipline, but data science is even more new, because it's the new science that is emerging that has to do with everything that relates to data. And this is not just computer science, this is not just statistics, this is not just about electronic engineering and networks and internet and high-speed networks that we need. It also encompasses social sciences aspects, because the data that we use and we draw insights are data about people, and the kind of techniques that we use affect people. So you need to bring in social sciences, and data science is a very interdisciplinary and multidisciplinary field that is emerging. So no one can claim it as its own. We have these discussions within my university between computer scientists and statisticians, and they all try to claim data science, but I believe that no one can claim it on their own. It's a much bigger thing. And now, of course, we have the hype around AI. And AI is a different beast. It can be considered as a subset of data science. It's a particular type of, if you like, set of techniques that we are developing. It has been around for a while, and I'll come back to that. But now it's getting a lot more prominence. And it's like everyone is trying to jump on the bandwagon. Everyone is trying to do data science or AI. And different things are being called data science and AI that perhaps should not be called that. So if you look at AI, artificial intelligence, and what was the purpose of the creation of the field, it was twofold. It was all about back in the 1950s when computers started being used in big corporations and big labs for a start, because they were at the time occupying large rooms. They were all about AI as a discipline. When we had the seminal workshop in Dartford College organized by McCarthy and other scientists, understanding intelligence for a start, and then creating systems with human-level intelligence. This is what AI was, at least at the time, conceived to be as the new area that was emerging out of computer science. Back then, people were very hopeful about what it is that could be developed in the next few years, and there were great aspirations and thoughts about having robots by the 60s and 70s that would be running our homes, and we wouldn't have to work anymore, and I wouldn't have to do any housework, but it didn't actually quite develop like that. So this is the birth of AI back in mid-50s, late 50s, that we have seen that we saw at the time when aspirations were at their highest and people wanted to make this work, and they wanted to deliver technologies that would benefit human life. So those were the early years, and realizations came along in that if you try to understand human intelligence for a start, it's very complex. And it's not easy to recreate human intelligence within a machine. So the realization was actually you cannot tackle this as one big task. You need to break down the problem into smaller kind of areas, and that's why we saw the emergence of computer vision as a separate area, natural language processing, speech recognition, machine learning, planning, reasoning, all of these, because people understood at the time that you could not tackle intelligence as one big thing. And because of these realizations, we saw the first AI winter, because people could not get their robots to clean their houses. And then we had another period in the 80s with the emergent, late 70s, early 80s, with the emergence of expert systems that were encoding human expert knowledge, and you had rules, you had to create all the rules in a manual way. And that's where the word expert, that's where the notion of an expert system comes, because you have all of these rules encoding human knowledge. And those systems at the time could give you good results if they had a really good knowledge base and good encoded rules, but they were unable to learn, they were unable to adapt to any new conditions or their environment. And that again led to another AI winter. So interest dropped, because expert systems didn't deliver what people were expecting them. And now we've got the big comeback of AI, Because now we've got what? We've got a lot of computational power that we didn't have before. Neural networks are not new. They have been around for 50, 60 years. We just weren't able to make them work because of the lack of computational power and the lack of data. So we've been able to make a lot of progress in aspects of AI, not the entire field of AI, because of the availability of data. And for me, this is important because we need to separate AI from machine learning, because there's a lot of confusion, and when people talk about machine learning, they equate machine learning to AI. AI is much broader than just machine learning. ML is a really important component, and you cannot have AI without machine learning, but it's so much more. There's planning, there's reasoning, there's searching, there's proving, there's perception and action, and so many other things that AI encompasses, coordination, collaboration, so many things. So it's not just about machine learning. And my own perspective when I look at this is that if you, linking AI with machine learning is if you really want to have truly intelligent systems, what makes us intelligent? Our ability to adapt. You put me, I came from the UK, I came to Brazil, completely different environment, different norms, different rules. I adapted. I can cross the road now in a completely different way than I do in the UK. Because as a system, I have the ability to sense my environment and understand that different rules apply. And perhaps I don't have to wait for the green little man to cross the road if no car is coming my way, whereas in the UK I wouldn't dare do that, but don't tell on me. So you have the idea, and we've heard about this concept of an agent in an earlier presentation. So this is your system, which can be a combination of software and hardware, or just software. You have the idea of an environment, and the environment is complex. It can encompass other agents. They can be humans, they can be other software agents, or it could be completely different heterogeneous agents. And the one in the middle needs to be able to cope with this complex environment. And then the agent gets sensory data, perceives its environment. This is the classical notion of AI. Something happens within the mind, within quotes, of the agent. There is some kind of database or knowledge base where facts, information is being kept, and then a model is being generated. There's machine learning or other processes that are taking place. And then action, a decision is being made, action is being generated, the environment gets affected by the action, and here we go again, we have another cycle. Now, there's a lot of, if you've done a 101 course on AI, you know that by the time you take action as an agent, the environment may have changed. So there's always this problem of how often do you stop to reconsider the action that you're about to take, but this is your typical AI. And learning is, in this picture, the process of acquiring new knowledge. And as human beings, we have different ways of doing that through imitation. We're being taught things like in school, or we use trial and error to learn new skills and to apply them in different domains. And hence why we need machine learning, which is powered by data. But as I said, there's more to AI than ML. And I want to pause here and talk specifically about the need for learning, because the need for learning that we have heard about today is mostly about predicting the future, predicting learning from historical data in a problem domain and making changes, making predictions in the future based on this data. For me, learning as a concept is a far more encompassing concept. If you have, if you're doing computer science, one of the modules, one of the courses that you will have done is in design analysis, requirements analysis. A client comes to you with a project, a problem, and tells you, I need an accounting system to be doing X, Y, and Z in my company. And what you learn as a computer scientist, as a computer science student, is you have to take this whole process, this whole project through this process of understanding client requirements, and then you design the solution, and then you implement it, you test it, you do user testing, you do black box testing, and all of that. And the problematic thing with this process, no matter what kind of model you use, waterfall model or whatever model you use, is you end up with a system that satisfies some of the user requirements, but typically not all, because things change. It's all about this change that happens between what you are being asked to do and the system being deployed. And we have really large projects that cost a lot of money that typically fail, or at least they don't deliver what they're meant to deliver. So imagine a situation where you start with this process, you produce a system for a client, and then the environment has changed, and instead of your system failing or not fulfilling all the requirements, the system is able to adapt and learn from the environment and learn to do completely different things and new tasks. So it's not just about predicting, but it's about adaptation as well. And this could revolutionize the way we develop systems. But that can also be quite problematic, because if you have a system that is adapting and it's learning, it can learn good behaviors, but it can also learn really bad behaviors. And this is something that some of the speakers earlier today have touched on in terms of the ethics of AI. But if you look at machine learning adaptation in this bigger context, then there's a lot more that can be said and a lot more that we need to do. And there are powerful reasons why we would like to have such systems in place. Because you may not be able to enumerate all the possible states that the system can find themselves in. So there are really good reasons. And as I said, very often you just cannot comply with the original specification because the requirements have changed. And you cannot just keep changing a system. So I'm going to go through some of these slides quickly, because I realize that the audience that we've got here, maybe not everyone that is online, has an understanding of learning. So we have different types of machine learning techniques, if you like, or families of techniques. We have supervised learning, where you've got lots of data and you're trying to train an algorithm to understand and draw insights from the data. You've got, so in this case, you have a labeled training and data set, and the task is typically prediction. You've got, we've got unsupervised, where you don't have a labeled data set, but what you are trying to do is essentially find hidden structures and patterns in the data through, for instance, techniques in this space. We've got reinforcement learning, which is a different type or a different mode of learning, where you are rewarding, you have the notion of reward. And we've got in between between supervised and unsupervised learning, you can have semi-supervised learning, or we have things like co-training algorithms, where you have limited labeled data, and you're trying to train with different algorithms and get insights from extracting from different types of algorithms. I want to link this back to the analytics techniques that I was talking about earlier, because there are different levels, and you may have seen this kind of description before. If you look at analytics techniques, so these are typically quantitative techniques that enable you to process data and draw some insights. You obviously are trying to draw as much value from the insights as possible, but then you have to consider how complex the algorithm is, and how difficult its application may be in a problem domain. So we've got, in the first instance, descriptive analytics techniques. And these are typically the techniques that you are using when you have a historical data set and you're trying to understand what has happened in the past. So the question is, what has happened in the past? You've got the data set, you're just trying to understand what happened. The next level up is, okay, now you understand what has happened in the past. You also want to see why it happened. So you're in the realm of diagnostic analytics. So you take it a level up. And this understanding is important if you want to move further up into predictive analytics, which is, okay, I have analyzed my data set, I know what happened, I understand why, can I use it now to predict what's going to happen in the future? As you climb up, you essentially increase the difficulty and the complexity of the methods that you are applying, but you draw more value. Because if you are an organization that is trying, for instance, to increase value for its customers, and if you are able to use predictive analytics, you are going to draw more value out of your data and the techniques that you are using, but they become more complex. And the final level is when you enter into what is referred to as prescriptive analytics. And this is beyond predictive analytics, where it's, let's try and predict the future. Prescriptive analytics is about how do you bring about the future that you want. So imagine a scenario where in the city of São José dos Campos, the government wants to create a new transportation system. They want to reduce the pollution in the city. Prescriptive analytics, if they had the power of prescriptive analytics, they could essentially be able to create what-if scenarios and create policies that would incentivize the citizens to leave their cars at home and use the new transportation system. So you're essentially guiding behavior in prescriptive analytics. So it's a lot more powerful, these techniques, if you're able to get to that stage. However, the problem is these are very domain dependent. They're very typically expensive to run. And they're very difficult and complex. And of course, wherever you are in this axis, there's no such thing as 100% accuracy, but the further up you move, the more difficult it becomes to understand how they work and the accuracy behind the method. So you move from information into optimization, and then from hindsight, which is looking at the past, into foresight in prescriptive analytics, because you're trying to incentivize behaviors, let's not say force. So it's a different, if you're able to do that, that's amazing. And I'm going to give you an example of how these techniques could work from a research point of view, so that you understand what I'm referring to. So I'm going to use an example of a project that we actually ran, which was a project we heard earlier today about trading strategies and using machine learning to predict. So we had a project trying to understand patterns in the foreign exchange market, and we had been given a really large data set of foreign exchange, essentially transactions where you transact different currencies, US dollars for reals or US dollars for euros, and you have these transactions in place. And it was a really big data set because it was in the millions of transactions of tick by tick data on a daily basis. So what we had was a data set, and from that what we did as the first step is essentially we wanted to see the kind of patterns that were they were emerging. Had we been a company at the time, we would be looking from this data set, from the historical data set that we had, to extract insights and inform action, like for instance how it is that we were going to trade in this market, or strategy, depending on the domain. So this was our descriptive analytics phase, where we were trying to identify patterns in the data. We moved a step up when we started considering, okay, these are the patterns that we see. Why is it that we're seeing these patterns? What is it that is happening? And we heard earlier about concepts around seasonality, and there are very well recorded, documented phenomena in markets, and we could see some of these in the data that we had at our disposal and the kind of patterns that we were able to extract. But we also went a step further, and we could see other patterns, and we essentially generated a theory, if you like, hypotheses, a set of hypotheses as to why it is that we were seeing these patterns in the data. And then from that step from diagnostic analytics, we moved into something different because the next step up is predictive. So can we predict, if we know the kind of patterns and when potentially they emerge, can we move into predictive analytics? Can we predict what's going to happen in the market? So for this purpose, we built a multi-agent system model, essentially modeling the foreign exchange market with thousands of traders, different strategies, again, based on the hypotheses that we had in terms of what strategies the traders were using that were generating the patterns that we were seeing in the data. So we were having the real data, we could run simulations, and we could see whether the simulated data coming from the artificial market were actually matching the kind of data that we were seeing in the real market. And that is a form of validation as well, because if you have a theory as to why you're seeing patterns, how are you going to validate it? You cannot go into a market and start playing with real money. One possible way forward is through simulations. So that took us essentially into the realm of predictive analytics. And the next step in this process, if we were to do prescriptive analytics, would be, okay, we have a full understanding of the market, we can predict what's going to happen next. If we want to change the behavior of the traders in the market, and for instance, avoid bubbles and crashes, what kind of policies can we put in place? And then we could have, if we were to do this step, we could have implemented the policies in the artificial market to observe the impact there, to then go to policymakers and say, if you want to avoid bubbles and crashes, here are some things that you can do that our simulations show they could work. So that's how it could work within this this ladder, if you like, or this step-based approach to analytics. But of course, getting to that stage is not easy. You need to have clean data. You need to have a lot of computational power to do thousands of simulations. So don't expect that this happened within a day. Someone sat down and created a model and everything worked fine. It took years. To get to a point where we have confidence in the kind of models that we have created. But if you're able to do that, that is, as I said, quite powerful. And these kind of analytics techniques, powered by the large availability of data, have made AI look more promising as a technology, and we have seen a lot of progress made in a lot of applications. We heard earlier today some of the, as part of some of the work that is being conducted here at ITA by students and staff in trading, in manufacturing, in different domains. And I've got some examples here. Some of them are local to the UK. So for instance, this image here shows a piece of work that was done taking input from patients. In the UK, you go to your GP, your general practitioner, and you get your National Health Service. If you have a cold, if you have flu, if you need a vaccination, information is being recorded about you, but patients have opinions as to whether the system works or doesn't work, or things that can be done to improve it. So you can collect this data and you can perform natural language processing to understand topics as they emerge in specific areas, if there are trends where you've got lack of services, for instance, so that you can target interventions. And natural language processing is a good tool if you have text data for this purpose. Earlier today, we were talking with some colleagues about work that we have done, for instance, helping our local authority, trying to identify patterns in knife crime, identifying vulnerable individuals like children, youth, young people that may be at risk of falling into let's say, illicit behavior, so essentially bad behavior, and you're trying to support them, again, through targeted intervention. There are all sorts of applications that you are familiar with. Amazon, we were talking earlier about big platforms, e-commerce platforms that are being used, and Amazon is using AI to some extent through collaborative filtering and other techniques to essentially match you with other customers. We have driverless cars. It's being used in these kind of semi-automatic AI technologies can be used in trading systems. All sorts of Netflix has been actually quite the driving force behind quite a lot of techniques around matrix factorization and identifying similar individuals. We have seen a lot of progress using neural networks in applications and in problems like in image recognition. And I've got some data here about how fast the progress has been in just a few years, simply because of the availability of computational power and huge data sets that we now have available, because we all upload photos. And what we don't realize is that once you upload it into a social media platform, actually the copyright may no longer belong to you. It may belong to the social media platform. So we have seen masses of progress in this space with absolutely astonishing accuracy, 98, and we are now playing with percentages that just don't make sense if you consider where we were 20, 30 years ago. So a lot of progress. Self-driving cars, I talked about this earlier. We haven't, I always doubt how a driverless car would behave, for instance, if it was trained in the US and then you put it in Greece or in Brazil, because the context is going to be very different. And though the driving rules may appear to be the same, actually they may not be precisely the same, and this raises all sorts of questions about the context where you put a machine or a system. We've seen a lot of progress in games, which is the traditional, if you like, AI platform for checking how fast you are making progress in AI and algorithms, with AlphaGo beating humans. So it's astonishing how much has been achieved within just the last couple of decades, I would say. It's really astonishing. I'm not sure I'll be able, I don't know if you've seen this. I'll see if I can. So this is robotics. This is Boston Dynamics, and you may have seen similar videos. I mean, this is extraordinary when you look at it. I wouldn't be able to do that. It's just phenomenal. So we've made a lot of progress, but what I would say, and I will come back to that, we've made a lot of progress in very specific domains and very specific tasks. You cannot take that robot, put it in water, and then expect it to learn to swim. It won't. But I would, if you drop me in water, I would probably start moving my hands and my legs, and I would try and rise to the surface. So it's all about this domain adaptation. And the rate of progress has been such that we have seen the field of AI being transformed. I did my PhD a very long time ago, and at the time it was during one of, I'm so old, during one of the AI winters, and people just didn't want to touch AI. Governments, research councils didn't want to give funding about AI, so it was a bit of an anathema. I'm not going to tell you in which decade that was, but you can see that since 2010, so in the last 10 years, we have seen a massive rise of papers, especially on machine learning and AI. So there's a lot that is going on in the field. And you can also see there, I've got a graph, I'm not entirely sure how clear it is, how many, if you like, the percentage increase in papers in machine learning and reinforcement learning, for instance, which is another big area that is emerging, how the papers have shot up. So there's a lot of people, there's a lot of work that is taking place in this very specific subfield of AI. And It's not just researchers. This was prior to the pandemic, so I have not had the chance to look at what has happened since, but as I mentioned in the beginning, there's this bandwagon called AI, and everyone is trying to jump on it. A lot of people are seeing the potential. We're talking about the potential to make significant difference in our lives as individuals and as society. And what you see as green, if it looks green from where you are sitting, is countries that have explicitly developed AI strategies. So we are talking about China, for instance, coming out with a strategy for AI. We are talking about the EU coming out with a strategy on AI. There's Brazil there, so you must have a strategy on AI somewhere. Now, some of this work may have stalled because of the pandemic, because this has hit the entire globe in a really hard way, though we have seen, again, the potential of AI making a difference, but it's massive. So there's a lot that is being invested on it, and this is just by governments. Lots of companies, businesses, organizations, almost everyone that I talk to as an external stakeholder, they want to do AI. They don't know how. As long as you give them something and you call it AI, they're very happy, I have to say. But we try to avoid this, of course. We are scientists. You cannot just sell anything as AI, but there's a lot riding on this. And for me, this comes with a huge health warning that I'm going to come to later on. So these kind of systems that we're trying to develop, it's very important to understand that they are not just artifacts. You're not just creating a vase or a computer or something. They are socio-technical systems. They are systems that are embedded in our lives, and they have an impact on us, and sometimes in quite unpredictable ways. So they don't operate in isolation. The data that are being used, they are pertaining to all of us, individuals, groups, society as a whole, and the kind of output that these systems generate, they also affect us. So it's very important to understand that when you've got them, when you've got such systems and they're being designed, implemented, and deployed by people within organization, they are being done so within a social, within a cultural, within a legal, and within an economic, and sometimes very country-specific context. And you cannot just take an AI system that we have developed in the UK and just assume that it's going to work in Africa, or an application that was developed in Africa, it would work in the UK. So we're talking about real people being affected by the decisions and the actions that these systems can take. And there are lots of issues. That's why I said this comes with a huge health warning. We've heard earlier today about biases, and bias is one. Daniela was talking about this. Accountability, fairness. I've got just a few things here that sometimes do make me wake up in the middle of the night, I have to say, and think, am I doing the right thing with my students? Am I training them to understand that it's not just about developing software systems and technologies, they need to understand the bigger picture here. And Daniela gave us a few examples of fairness, and I'll come to that, but fairness is a concept which is very abstract, and it's very domain dependent, and it can mean a lot of things to a lot of different people. And AI can provide the quality of opportunity, or it can deprive opportunities from specific groups, depending on how it is being applied. We can have marginalized groups being identified by AI systems. Daniela was telling us about the example of Compass in the US, where essentially, because the data set was biased and it was all about Black and ethnic minorities and other marginalized, perhaps, groups, of course, the algorithm was predicting that someone of color will be reoffending. So it's very important to understand all of these things. And then we talk about ethics and trust and privacy and all the data that we leave behind and how much we are leaking as individuals and what people can do with our data. And there are other more fundamental problems, like, for instance, learning being considered as a black box. Because I showed you this earlier, what happens in the mind of the agent with some of the algorithms that we are developing, some of the techniques, we don't know what is precisely happening. We don't have a full understanding as yet as to why we're getting really good results in some cases, but not necessarily with a full appreciation of why the algorithm works the way it does and why it gives us that result. So obviously, the quality of the algorithm depends on the data set, and we talked about biases. Daniela has already talked about the different categorizations of biases, and I have a couple of slides, so I'm not going to spend a lot of time. Basically, you can have bias being introduced in different stages, if you like, of trying to apply machine learning in particular. So you can have it when you're collecting the data set that you are putting together is, whether you like it or not, a historical data set, unless you update it on a continuous basis and it's a streamed data set. So you can introduce bias there because you may not have a true representation of what is happening right now. You can have the representation bias because the population, the data that you have collected may not be representative of the whole population. Measurement bias in terms of the features that you're using and the labels, and they may not be representative. Or you may have aggregation bias, because very often we tend to aggregate data, but you may not capture in this way subgroups, or evaluation bias, depending on what kind of data sets you're using for evaluation. You may be introducing bias there, and of course you can have deployment bias because you're of the way that you're deploying the system, which may be for a different reason than originally intended by a researcher. And then we start having confusions between correlation and causation, and I really like this one because it almost says, okay, if you have a cat, if you own a cat, you will probably be struck by lightning. There's a, you can say this, you can try and link correlation and causation in this way, and we can see really big problems emerging in this space. And no matter how good your data set is, if you are trying to essentially get really good results out of your algorithm, of course you may end up overfitting your algorithm so that you can get your good results. But then if you put it out there in the real world, what can happen is the real data may be very different to the artificial data that you have been testing and evaluating, and you may end up getting completely skewed results or unexpected results. So how do you define fairness in this context? What does it mean? We can talk about, we can give it economic, if you like, definitions, like based on notions of social welfare or Pareto optimality, but it could be different things. It could be statistical notions, as Daniela was describing, or you can start going down the route of legal definitions of fairness and fair practices. You can start talking about protective characteristics, how you present these in your data, how do you make sure that you don't discriminate. So there are lots of questions that are emerging here, and perhaps we don't have all the answers yet. And there's no universal definition. Because very often we use these terms, but they are quite abstract and, as I said earlier, quite domain dependent. I'm conscious of time, so I'm going to try and bring this to a close soon. Accountability and transparency are two really, really important things when we talk about machine learning and data science techniques as well as AI. In my view, and perhaps I'm too old, and that's why I'm thinking in this way, is that these technologies can be quite powerful. They have a lot of potential. We are not always clear as to what it is that they are delivering, so it's very important to have the humans in the loop. because if you don't have them in the loop, you can end up in a really sensitive application where, for instance, hypothetically, you have data sets about families in my region and you're trying to identify vulnerable children or vulnerable adults. And if you don't understand the outcome that the algorithm is giving you, you can end up misidentifying individuals, placing children in care when you don't have to. You shouldn't be doing that, which can have really catastrophic results. And this goes back to what I said earlier about these systems affecting real people like you and me. And all AI and data science solutions, and this may be a bit controversial, in my opinion, they need to be explainable. We need to be able to say why it is that we're getting the result that we're getting out of a system. In the EU legislation and in the UK, you've got this embedded within the legal frameworks. If a company is using an AI algorithm, for instance, to provide insurance, health insurance for individuals, they need to be able to explain how it is that a quote is being generated, how it is that a decision has been taken, for instance, to reject an individual. And this is really, really important. And we've got, as I was saying earlier, the more complex the technique, obviously the more difficult it is to apply it, the more domain dependent it is, but also when we have some of these really complex deep neural networks that are getting outputs and inputs and they're combining them in all sorts of ways, we may not have a complete and full understanding of what it is that is generating the result. And their explainability, so this is a new area that has been emerging in the last few years, is really important. And we have, when you look at simpler techniques like decision trees, you can trace, you can track how the decision has been taken because you can go back to the algorithm and you can see. But for some of the more complex neural network techniques, they're far more complex to understand. And where we want to go is essentially to, there's a typo there. It's not autonomous, it's autonomous. Trustworthy and responsible systems. This is the terminology that is now emerging because we want these systems to be accountable. We want them to be able to explain their behavior. We don't just want them to be smart, to be helping us, but we want them to be accountable. And there's a huge, there's lots of work that is going into this. And if you recall earlier, I was talking about the software systems that are able to adapt and modify their behavior. So imagine you are one of the software developers that has contributed to this work. Who would be responsible if a system that you have helped develop has learned new behaviors and now suddenly it has caused a major problem? Would you be responsible as the developer? Would the user be responsible because the system is learning from the user's behavior? Who would be responsible? When you start thinking about these systems as more complex entities and being able to adapt and evolve, there are some of these questions that we haven't even begun to answer. But this is not necessarily a piece of work that we can do on our own as computer scientists. What we need here is a more coordinated effort with social scientists and those that are working in the domain of law, for legal frameworks, and even human rights to get down and talk about how it is that we can resolve these problems. We're talking about synthetic societies in the future, societies that obviously include us as humans, but they include these systems that could be semi-autonomous or fully autonomous. So what kind of norms and institutions are going to emerge is, well, it's an unresolved question and maybe something that we all need to work together. I just want to give you a couple of, I'm going to talk very briefly a little bit about my experience, if you like, as an academic working with organizations that want to embed data science and AI within their practices, and some of the problems that we've had in this respect in the UK, and I'm not sure if this is the same here in Brazil. But typically when we are in academia, I'm an academic, my role is to undertake research and to educate my students. A company comes to me or another organization and says, I have a data set, I wanna work with you, I wanna deploy AI on this, in this domain, how can we go about and we can work together? The problem is, when you are working in this kind of context, there's a lot of regulation that you need to comply with. So for instance, in the UK, it's very difficult to get access to real data about, and I'm not suggesting that this is wrong, but it is problematic when you are trying to develop applications that will go out in the real world if you don't have access to real data to test techniques. Because obviously some of this data can be confidential. And you can try and put in place what we call data sharing agreements. So I can sit down with a business and we can draft a data sharing agreement that will say, Maria is not going to share the data beyond this project, and this researcher is not going to do X, Y, and Z, and the data set is going to be held in a secure environment, etc., etc. But actually, sometimes these data sharing agreements take an awful long time to put together, at least in the UK, because the people on the ground that do the research and do the work have to interface with legal teams that have a completely different understanding of the law and appreciation of the work that we are trying to undertake. And sometimes obstacles are put in place that is very difficult to overcome. And I've got an example of a business that we have been working now for the last 5 months to try and put together a data sharing agreement, and we had legal teams from the university and from them sitting down, and the researchers from both sides were saying, please find a way so that we can work with each other. We just want to work on anonymized data sets, and both sides were saying, no, this is quite dangerous. So it's been quite difficult in this respect. We have things like data archives where you can place confidential data sets and you can work on them, but these have their own problems because these data sets tend to be static, and you're looking at historical data sets that may have been relevant 2-3 years ago. For instance, census data that is being collected every 10 years, but census data collected 10 years ago is not giving me an accurate picture of what's happening now. So that is problematic. And I understand all of that, and there are lots of sources of risk when you're dealing with data, and this is one of the health warnings. And one way to try and understand the problem here is to use what is called the 5 SAVES framework as a way of identifying the kind of risks that you can face through data access. And you have to ask yourself are we talking about safe projects here? Is the data use lawful? For instance, I cannot take National Health Service data and make decisions about insurance. This would not be allowed in the UK. Safe people, we talk about safe people. Are the researchers that are working on projects to be trusted? Have they had the right training? Are they using data appropriately? We're talking about safe settings. Does the manner of accessing the data offer protection? Do you completely take out all individual identifiers? Postcodes, for instance, in the UK can help you identify individuals or families if you try hard enough. Safe data, is there a way that you can protect the data itself and safe outputs? So the typical example here is you perform your analysis on a data set, you publish a paper, you include some of the results, and then the outputs, the paper itself, because it talks about the data, it can be used to identify individuals. And what we are working on right now is a slightly different model because of these problems, where instead of typical machine learning works in the following way. You give me a data set, I host it on my platform, I perform the computation on site, I give you the results. There are new approaches that are emerging and actually emanating out of Google, federated learning, which essentially enables you to take the computation to the data. So you don't take the data out of the platform that is sitting, say, hypothetically in Essex Police or a government organization, but you perform an operation remotely that has already been pre-approved, say, by the police, and you don't get access, direct access to the data set. What you get back is intermediate results that help you train a model. So if you're interested in this kind of work, it's, I would suggest you look it up because it appears quite promising. So essentially you have data, this notion of a data controller and a data owner, but the data owner does not essentially give you access to the data itself. So, I mean, there are always risks of identifying individuals even through this process, but it's less risky than other approaches, let's say. So I'm wrapping up now. So I just wanted to bring things together. AI is not just ML. There's the risk of oversimplifying artificial intelligence and overhyping it as in terms of what it can do. And I want to pause here and make this comment and be quite serious. AI and machine learning, they're not fairy dust that you just pick out of a jar and you throw it on top of something and magic happens. It doesn't work like that. And we need, it's within our remit, if you like, as computer scientists to educate businesses, organizations, but also the public about the potential as well as the perils of AI. And we, you know, someone could turn around and say, maybe artificial intelligence is like the alchemy of our time. We're looking for something, some kind of technology that will create marvels. But we haven't made progress in general artificial intelligence. So the Terminator is not around the corner, not at least within the next 10, 15 years. I would be surprised if I see a Terminator running down the street, because we have not seen developments in areas like reasoning that are required to make this kind of progress. And of course, everyone is looking for the ideal data scientist, which is not one person. It's multiple people and different people called data scientists, different sets of skills. And you may be looking for someone with expertise in NoSQL databases, and maybe this is your data scientist, or a data engineer, or your machine learning person, or someone else. But it's not one person that has all of the skills that are being required in this space. And if you believe it is, then it's like you're looking for a unicorn. And I have not seen a unicorn in real life. If you find one, take a photo, email it to me. It would be really good to see one. And I want to end up with who is benefiting from these technologies, because very often we take it for granted who is benefiting, and we've seen this as part of what happened during COVID. You know, the developed world saw, if you like, the outputs, the outcomes of research much faster than other countries. We still have millions of people that are unvaccinated in Africa. Here in Brazil, amazing progress, but in Africa right now, the majority of the population is unvaccinated, and it's the same with technologies. Not everyone has access to these technologies. So if we want to democratize AI, we need to think seriously as to how it is that we're going to enable everyone to have access to these. So I'm not going to repeat these. I'm just going to thank you for your patience. I have not heard any snoring, which was a good thing, and no one has indicated that I have walked or talked very fast, and I'm grateful. Thank you.
Thank you, Maria. Now I'm going to open for questions, please. Feel free. Enjoy this time all together.
Or a discussion.
Yeah,
I don't have all the answers.
A question and discussion. We are going to open for any point, any questions. I'm going to keep with the microphone and ask you, Maria, to use this one.
Hi. in the beginning of your presentation, you talked about human level intelligence. However, the way I feel about artificial intelligence is about achieving human level performance. So how do you see that? Is all about intelligence or performance as well?
Well, as I said in the beginning, that was the original purpose of AI, to achieve this human-level intelligence. In some of the tasks that I have demonstrated, we have definitely achieved human-level performance, but again, it's in very specific tasks. We can have robots that have learned to jump, but as I said, you throw it in a pool of water, it's not going to learn to swim on its own. You will have to tell it. You will have to retrain it. It's a very interesting question that you're asking, because we may have to come to terms that we may not be able to achieve human-level intelligence with current technologies. And I'm talking about the kind of digital technologies that we are using. It may be that we can make a lot more progress with quantum computing, because that will enable, it would be a completely different paradigm of computing, and it would, and I have to profess I'm not an expert, so don't start asking me questions about quantum computing, but I've had conversations, and if we are, the cost of quantum computing is coming down. There are companies that have developed quantum computers, and we may be able to have breakthroughs through quantum computing to get us, and maybe we are going to see the Terminator through a quantum computing machine rather than a digital machine. So we have achieved human-level performance, not necessarily human-level intelligence. We may not be able to get to the human-level intelligence with current technologies, but perhaps there's something else. Or we may have to come to terms with the fact that intelligence is so complex to reproduce, and we don't understand all the mechanisms behind yet to get to where we want to go. And that was why AI failed in its original, if you like, goals early on, and unfortunately disappointed.
Yeah, I really wasn't thinking about achieving human-level intelligence by new hardware or new paradigms, like you said. So thank you for the answer. It's very aggregating. Thank you.
Oh, next one.
Hello. Thank you for your presentation. Very nice, very inspiring, several interesting things. You mentioned about big data that is a concept, and that it's really interesting ontologically thinking about it. There is a need, a specific need to concretize big data, right? It's a concept, but in fact, to talk about big data, we need a very well-defined infrastructure for it, right, ontologically speaking. And the slide you presented, SLEDge and somebody else, I can't remember the name, about bias in every stage of data, right? That's really interesting. And talking about big data, and at the very beginning of that process, about historical data process, something like this, right?
It was historical, the historical bias.
And the bias can start there, right? And in the case of big data, in which we need that infrastructure to concretize big data, my question is it much more difficult or more, let's say, more problematic in the context of big data bias at the very beginning?
That's a really good question. I think big data, especially if you talk about stream data, may actually provide a way forward in terms of the historical bias that you can have, because if you have a continuous stream of data coming in, if you like, it's current data that you are getting, it's not historical data, and depending on the timeline, that may be one way that you can avoid having this historical bias being introduced at the beginning. With big data sets, and depending on how representational the data set is, you may avoid some of these biases, but you still have to check. At every step of the process, you have to check. But I think as you are asking the question, I'm thinking in stream analytics, for instance, you will have a continuous stream that is coming in of data, and provided that it's representational of what's happening on the ground, the historical data may at least be minimized, if that answers your question.
Yeah, yes. In my view, the situation is much more complex now in the big data context. Because in the past you used, a smaller set. Now we are talking about integrating different data from different sources, from different formats, and that's why I think it's much more difficult. Bias can be introduced in a more complex way than before.
Yes, absolutely, and that's why you have to be vigilant and check at every step, and not just take it for granted that you know what you're doing, because it's not the case that we are in control of all of these biases. And a parenthesis here, so what is, one of the things that I had to do before I left the UK was I had to renew some of my training, as an academic, and because of the position that I hold in the university, I have to go through regular training. And one of the training courses that I had to do, you are probably wondering why on earth is he talking to us about your own training? You'll understand in a minute. The training was about automatic biases that we have as individuals. So it's commonly known, you apply for a job, you go into an interview, the people that are interviewing you are making a decision within probably a split second on whether they like you or not. You don't even have to open your mouth, because that's how we work. That's how we operate as human beings. We have our own biases, and that's why it's now being called automatic bias. It's not unconscious, it's automatic bias. We have it, and you have to be able to recognize it to avoid it. And it's almost as if we need to avoid these automatic biases in these software systems and hardware systems that we are developing, because we're just introducing biases all along. But for me, it was quite fascinating, because I was given, I was shown photos as part of this training, and I was shown someone who was wearing, their hair down. It was very all over the place. They were not wearing a suit, so if you like, their dress was not what I would expect of someone coming in to interview. And I was showing another photo of someone, in a suit, going into an interview, and I was asked to automatically, within seconds, say who would look more professional. And of course, I went for the person in a suit. But the other person can have perhaps even better skills than the person who is wearing a suit. So what I was being asked is to recognize that I have this automatic bias, because this has been built in me as part of the interactions that I've had, and do something about it. And that's what this is about. We need to recognize that we are building these systems with bias, because we are biased people, and then we can do something about it, if that makes sense. So I hope the connection makes sense. If you just let your biases enter into really complex systems, and systems that are making very sensitive decisions about people, then you are in really dangerous territory.
Okay, thank you. Okay, just one question and then go there. Okay, okay.
So, Professor Maria, thank you for your presentation. And at some point in your presentation, you talked about that the technology or the algorithms, machine learning algorithms and artificial intelligence, it comes from the early 80s or 90s, for example. I have somehow the impression that we are somehow collecting the result from the research in old times, but we are not really evolving to new concepts. Can you tell your opinion about that? Because I just, for example, I can see some development, new developments, for example, in the area of causal inference. There is a break in this point, but when I go to for example, deep learning or neural networks, they are really old algorithms, but now we have the computational power and technology to support this technology. So if you could give your opinion about that.
So we have certainly seen new algorithms emerging, but what I was trying to say is that some of these algorithms, they are based on older concepts that have been around for a long time, but at the time we were just researchers, weren't able to make progress. So for instance, natural language processing has benefited a lot from deep learning models. So I'm not trying to put down the work in machine learning or deep learning that has been evolving. And you're right, we are now seeing progress in areas like causal inference, but there are still problems there. We have not solved everything. But we need to make a lot more progress in other fundamental areas of AI, like problem solving, like planning, like reasoning. For instance, we have seen very little in reasoning. So all the focus has gone into ML, and people believe that, and that's why I try to make this distinction. ML is AI, ML is part of AI, but AI is much bigger as a field, and we just, we all need to work together if we want to make a lot more progress in this field. So there has been a lot of progress. There has been a lot of progress in new algorithms, in taking concepts from the past and completely reinvigorating them and coming up with new ideas. Absolutely, I would not put that down, and I'm thankful, right? Because I can now use Google Translate when someone here in Portugal doesn't, someone here in Brazil doesn't speak English and I'm trying to communicate because my Portuguese is horrible. So I'm grateful for all of that, but there are so many other problems that need our attention.
Okay, thank you.
Please, anyone more?
But I would set the challenge back to you, the younger generation, to make that progress. It's not, I'm going to hopefully retire at some point in the future. I'm not going to tell you in how many years, but it's down to the younger generation to come up with the new ideas and give us these breakthroughs that we need.
Professor, I have first to explain my question. I would like first to make a sentence. Every data and everything that we can sense is biased. Everything by our reality or economically talking by capitalism and by our social structures, and how we can differentiate just the bias from the context, or how to deal with this. Do we have to identify bias? Do we have to avoid bias? What's the right or desirable position that we have to take front of bias? That's my question.
So that's an excellent question. And if I could give you a full answer, I think it would be amazing, but I won't be able to give you a full answer. I think step number one is to accept that the kind of systems that we are creating, whether we like it or not, will include some kind of bias. And the second step is, once you accept it, to start thinking of ways where you can address it. So that's why I said, for instance, have the human in the middle, have the human in the loop of the decision making, so that you can check things, you can provide assurances, you can have explainable AI, you can have explainable algorithms so that you can check. So I don't think we will ever be at a place where there isn't going to be any bias, because the way we are made, if you like, as human machines, and the way we see the world is biased. But the least we can do is recognize that we are. The systems that we develop will have these biases, so let's do something about it, recognize it, and it can be addressed at different levels. So a policymaker, for instance, can ask someone who has developed a system that gives a recommendation for a policy on to do X, Y, and Z. How is it that the system has generated this? Can ask critical questions. Am I disadvantaging specific individuals? What will be the impact on marginal groups, on specific groups of this policy? So all of us need to start asking ourselves these questions. And this is not just us as computer scientists, but it's also the public. And I think it's important to educate the public as well about the potential and the perils of this technology, so that they can question when a decision is being made about them. When I'm being told that I cannot have insurance, I need to ask why. Does it make sense? So there isn't, I wish I could give you an answer of, if you do this, then you're not going to have any biases, but there isn't a silver bullet, if you like, that will resolve this.
Yeah, I understand, and it makes part of being human and social biased. So the second question I would like to do, if there is time, about the data sharing and how to make contact with social or manufacturing or politicians, and how this negotiation starts. Because a little time ago I had some situation with this, and I would like to know how to initiate and start this negotiation with, if there is any reference, or how can we researchers start to make this negotiation. Because we see that in many times we are constrained by our poor capacity of dealing with this problem.
Okay. So your question, I think, has two parts. The first part is how you initiate contact. So how do you, I will rephrase it, how do you raise awareness, for instance, of the skills, the expertise that exists within an organization such as ITA, so that businesses, different types of organizations can approach you, or you can approach them. And there isn't one single way that it would work. You as an individual or an academic or a researcher can make direct contact. Events such as these can help raise awareness of the work that is taking place within an institution. One of the things that I have done, and it has worked quite well in the UK, is if you know that there's a specific sector out there, say, I don't know, marketing companies that could use the skills that you've got within a university, how do you initiate contact? Well, we organize, for instance, what we call breakfast events, because obviously you cannot expect these people to be perhaps coming along to an event that is going to last 5 days because they just won't have the time. You need to entice them to come in and give them a little bit of information before they decide that they want to work with you. So we organized breakfast events. So you advertise in a sector that you're going to have an event which is going to be a couple of hours in the morning. You offer breakfast to businesses, say manufacturers, to come in. You organize a set of presentations, not at a very technical level with a lot of symbols and a lot of formulas there, but simply to demonstrate the kind of skills that you've got, so that you can show them the kind of, if you like, benefit that you can deliver for them if they work for you, work with you rather than for you. And that's how you can start, you can initiate a collaboration. If you have specific contacts in an organization, then it helps. You can make direct contact and you can talk to someone and you can explain your work. But what we have found is, obviously we are academics, we are researchers, computer science students, graduates. We like to talk a lot about the technical details, and sometimes the kind of people that you talk to in industry, for instance, they may not understand all the technical details, so the kind of language that you use is really important. It needs to be pitched at the right level, because otherwise you're going to lose them if you start giving them, how many rounds of simulations you're doing and what kind of p-values you have. You're going to lose them. You have to give them the bigger picture. And then on the data sharing agreement, you can find, so in the UK there are standard data sharing agreements, and these are available and you can download if you search data sharing agreements or collaborative agreements. There are samples out there that you can use. But the problem is, as you rightly pointed out, the negotiation bit. And you as an individual, or even with your PhD advisor, may not be able to negotiate this at this level. You may need to reach higher up in terms of a head of division or a specific section that you may have within ITA that looks at contracts, because obviously each side needs to protect itself, and we're talking about IP. Intellectual property rights that need to be secured on both sides. So that's why it takes time. And when you talk about data sharing, depending on the country that you're based, there may be legal requirements as to what it is that you can share and you cannot share. So in the UK, there are things that you can, businesses or organizations just wouldn't share with us. Because if there's a risk of identifying individuals and sensitive data, you just cannot risk it. But it takes time. And that's why a lot of there's work that started not necessarily to try and address this specific point of data sharing agreements, but still trying to protect people's privacy when they're sharing data. This aspect of federated learning, this federated machine learning that is emerging now, which is, it has some potential as an area to overcome perhaps some of these issues.
Thank you for your answer. It was very explicative.
Thank you.
So we are running on time, and I have one question by myself. Sorry. Let me make my question before I don't have any time. At ITA, we are very concerned about the concept. We teach theory, we teach mathematically, statistically, how to work on AI, on data science. We have a statistical part, other part, we have computer science. Our postgraduate course are very dedicated to work on formulas instead of just deploy this one platform. However, some of our students face difficulty to communicate this to the market. When you go to the job market, I stayed there studying AI data science for 2 years. It's why don't you make a short course of 40 hours? You find it online, or you can do this you can study this during your weekend. I think that you have wasted your time there. But actually, such a course is just input in a formula, in some sort of some function in Python or and get the results. They don't teach the concept. It's hard and difficult to communicate this to the management, to the manager. Okay, hire our people, our students, because they are well prepared for this. How do you face this in England? Do you face such a situation in England that you have to explain that's not for dusty, that you in 40 hours or stuff that we learn it?
That's a really good question, Elton. You left it for the end. So,
a provocation.
There's two ways you can train a data scientist, as you said. You can take them through a proper course, and as you said, it's all about teaching the concepts. And it's about teaching, for me, the fundamentals and the principles, and the principles and the fundamentals are transferable. And no matter what language presents itself in the future, if you understand the fundamentals of data algorithms and what's happening in a machine, you can transfer this across. You're right, some organizations want to have quick fixes. They want to have someone doing a 40-hour, sometimes they ask us for 20-hour courses, and get them to a stage where they can be the perfect data scientist, being able to do everything. And it's very important that you clarify expectations and what it is that they expect the individual to do within an organization. And you have to be patient and persistent, I think, because obviously businesses, time matters and time is monetized. But there are different ways that you can try and work with them. So one of the things that we are trying at Essex is to have this idea of short courses that you can essentially combine to get a degree at the end, but by doing it in a kind of modular way, but without losing the science behind, because the science is important. And that is really important to explain to employers, essentially. What is it that you want? Do you want someone who can fix the problem today, but then if you ask them to fix a different problem in a week's time, they just won't have the skills? Or do you want someone that will be able to fix problems in the longer term because they understand the principles and the concepts and they can move from one language into another, or they can have the much deeper understanding so that they can get additional skills in an area as it develops. And it's all down to the kind of person and investing in the workforce. And in the UK now, even organizations like NHS, the National Health System, wants to do what they call workforce development, which is a longer-term goal. It's not about just giving them some skills that is going to serve them now. It's the longer term, and it's lifelong learning. And the government actually have put in place a pilot which hasn't started yet. They're commissioning projects as we speak to try and facilitate this for individuals, because as we have a first degree, we come out of university. Not everyone comes out of a university and they want to upskill themselves, but they want to upskill themselves with the right skills, as if you are going through a proper university course. So in the UK, they have started thinking about how it is that you can deliver university courses, but in a different manner, and not in the traditional 3-year or 4-year or 5-year programs. But that goes back to making it clear that the kind of people that you will be getting out of an undergraduate program or a graduate program from a university will be very different to someone coming with an online course from X, Y, and Z. And I'm not putting down online courses because they can be valuable, and actually there are individuals that can learn a lot and they can get to the same level as an undergraduate student by just doing courses online. So I'm not going to suggest that this is not possible. It can be possible, but there's There's a very good reason why we have universities, because they provide a formal structure of learning, and they provide you with the principles that you need to become a long, if you like, a professional over a period of time, rather than someone who is able to do a job now, but then you don't have the skills to do perhaps a modified job in a couple of years' time. So it's not easy, but it's about trying to understand their needs, and if their need is we have to fix a problem now, rather than get the longer term investment, so be it. But we are here as universities to provide the essential skills of the workforce, but in a coordinated manner and in a principled manner. And the kind of principles that I was taught as a computer science student, they have stayed with me. I mean, the kind of problem solving that I was taught, the algorithmic thinking, what is now referred to as computational thinking, that cannot easily be taught by just essentially attending online pre-recorded lectures. You have to do it in a different way. We put the students in groups to solve problems, to exchange ideas. And if you lose that from the education system, then I'm not sure what kind of graduates we're going to get at the end of the day, and how useful they're going to be to society, to be honest. Maybe I'm quite a traditionalist.
Yeah, maybe I'm also quite traditionalist as well. Okay, one last question, please. Okay. Okay, sorry. Okay. And the last one, okay? Thank you. Thank you, Rob.
Thank you, Professor, for your... you and Daniela talk about bias regarding data provided by a human, right? About diversity and ethics and minorities, and I think now we have this awareness about this subject. But many of us work with data provided by machines, and I mean mechanical and electrical data. And I think about this kind of data, we are concerned about transparency and another kind of situations. And I would like to know, what do you think about this? What kind of concerns we have to know for the future about this kind of data?
So do you mean data, for instance, coming out of Internet of Things devices?
No.
For instance?
About, I don't know.
Give me an example so I can...
So you have a machine and you have the data like pressure, temperature. So you use this kind of data to maybe create a model to classify the accident, this kind of problems, you know?
I'm not entirely sure I can think of a scenario. So if you've got machines, so imagine you've got, I don't know, thermometers in a room, like this one, or other sensors that are essentially recording data. So a thermometer or a thermostat is recording the current temperature. How is the question then, how do we make sure that this kind of data which are being generated by a machine?
No, my question is, we are now thinking about how to make this personal data more transparency and more ethical. So with there any thoughts that we have to think about this kind of another data, the machine data or not? Because I think for you have this kind of property industry, and you have to a lot of knowledge there is only for my company. So if I could share this data, maybe another company could improve their models, I don't know, their process. So you think we should think about transparency for this kind of data too? Or not? It's not a...
So, but are you talking about transparency, or are you talking about open data?
Any kind of...
Because I mean, any business that has data, obviously the data have some kind of value for the business. And that's why they don't typically want to share this data or open up their data. There is an open data movement which a lot of companies and public sector organizations are working towards, but you cannot have all data as open data, because there are sensitivities in the data. There may be sensitive data like, you know, my National Health Service record, for instance. No matter how much I want to help the community of researchers research about diseases, I would be reluctant to have my full record opened up. So the answer, in a way, is it's very domain dependent. And every domain you will, and any organization will need to look at what data they've got and what will be the risks of opening such data to the wider public. Where there's a lot of potential for open data, and we have seen this in the UK, when organizations just make their data available and different people create applications that otherwise wouldn't be possible, but it should be data that don't put individuals or groups at risk, if that makes sense.
So we are running out of time. I really appreciate your time, you appreciate your presentation, and I'd like to thank you again and for the competitive as well. So just remember everyone that tomorrow, okay, let's use this one. Okay, it's better. Tomorrow at 9, we return back here with the data science and the pandemics and the project coordinated by Dr. Ana Carolina Lorena. In the afternoon, you're going to have the Women in STEM meeting. All that is going to take place in this room. And for everyone, postgraduate students and the graduate students, undergraduate students that are interested in academic area and research, on Wednesday morning and between 10 and midday, we're going to have a discussion and a roundtable here and to discuss the postgraduate study, research, the academics, future in academics, and the work after you are studying, international cooperation, international opportunity. So don't leave us tomorrow, Wednesday morning, for all postgraduate students. We're going to have this such of opportunity. Thank you all. Thank you for your time. Thank you for the people on the transmission because they are out of the hours. And I'm sorry for the short delay. I see you tomorrow. Thank you.